Hey everybody, it is Mega Mondays. We've got the Mega Man shirt on. How is everybody doing this morning? I should ask a question to start. That's how I should see like if you guys can hear and see me. We were just asking in the chat. Good to see everybody. So how is everyone doing? I see tired. I know, I feel it too. I feel it. No, it's like good morning, tired. Got a lot of good morning, tired. Everybody is tired. Everybody is very tired. We got very that is the theme of the day. No, we're gonna wake up right here because you guys know what it is. Today is you called it. Get ready for it. Today is Mega Mondays. So we got some new stuff today. Once again, if you didn't catch it, today is wait for it, wait for it. There's our guy right there. There's our class mascot, Mega Man right there as I go off the screen right there. So Mega Mondays, let's go. We got this. It's Mega Mondays. So how does this work? Well, wait, I can't do that one yet. I'm not on the right screen for it. But I love Stat Nation. We gotta start using that. So, and points should. Oh, Streamlabs already doing it because I don't know why it takes a while sometimes. I don't understand these things. They work. And if you notice, does anyone notice that their points took a jump? I added in all the 100 points. Please tell me if you think I can kind of see like I can see where I jumped people's points. But if you notice your points took a jump, they should have because I went through this weekend and I added in all of every. Whoa, I'm just gonna hit the microphone. I added in all of everyone's extra credit. Do people's points now look like they took about a 100-point jump? Some people's 120 do the extra credit. Everyone's checking points now. Streamlabs, where you at? Streamlabs is doing it now. Keep up with the Streamlabs. Everyone wants to know their points. Yes. And wow, people are doing amazing. So we got some people saying, yep, got yeses in the chat. Good. So I'm able to do that on the back end. Remember, please email me. Try to do it after class. So that way I don't get an email at the end of the semester being like, hey, Brian, I got like 200 points from Mega Mondays. Well, there's not even 4 Mondays. So remember, you can, when I give out the 20 points on Frenzy Fridays, I got to make a graphic for that. Today, once again, I love the new graphic, the Mega Monday. These are my favorite Mega Man right there. So Mega Mondays. And I did that text effect. I don't know. That was, I have fun kind of doing this stuff. We got some amazing points in the chat right there. But you should see your points have a jump. And Streamlabs is working overtime. Streamlabs, you get 50 points right there. Streamlabs is the first one to get some Mega Monday points. Did you like that the crash intro? I had to explain that one to Jason. Jason, my graphics and awesome dude, made that. I had to explain Crash Bandicoot to him. I had to explain like we are number one, and I showed him that with Crash Bandicoot, and he was like, I don't get this, and I was like, don't worry. I was like, they'll understand Crash. Now that's like a 2018 meme though, but that's still classic. Awesome. Streamlabs is awesome. You can even tag Streamlabs. We'll probably break it or something. Okay, it's what the kids want. It's what the kids want, Jason. I can't. Crash is timeless. I might start playing Crash Insane Trilogy. Red Dead 2 just went on Game Pass, so I downloaded that 101 gigs, but Comcast has all you can download. Any questions before we get started here? This is our first 5 minutes of class, just relaxing, knowing what's going on with the world. Today's Mega Monday. We'll be giving out some big extra credit here in a moment. I've got some ways of giving out some fun stuff. Oh, I'm so sorry. I am Xbox, yeah. No PC. Well, I mean, I have played some PC stuff. I was PC growing up. And then I've switched, Nintendo Switch also. I thought you said DDR2 for a moment. Oh, Red Dead 2? Red Dead Redemption 2? Yeah, that's what I figure. It's probably going to get me working on that. So I liked Red Dead 1. Newest Crash is really good on PS4. Yeah. I want to get a PS5 when that comes out. Hopefully everything goes swell with that. So, swell. That's the word. Takes like 60 hours to beat. Awesome. So yeah, I'll be checking out some Red Dead 2, but we won't see you for 3. No, the only time, this is my last comment on that, and we'll start getting serious here. The only time you would not see me is if I started playing like World of Warcraft or something like that. Like if I started an MMORPG, but I don't know. There was ones I got into. I got into The Realm, Maple Story. People have probably no idea what The Realm is. Look up The Realm from Sierra if you want. Yeah, I'm too afraid to play things like WoW. Like, yeah, it's dangerous. I'll be like, hey guys, and be like, Brian was up all night playing WoW. Like students start going onto my server and they're like, hey Brian, you need to go to sleep. It's 6 a.m. We need a little bit of awake Brian. We need Brian to stay awake. Taking a deep dive within yeah. So that's probably my biggest advice for gamers is watch out for MMORPGs. I'd probably be Alliance, my first Soldiers of Fortune. That's I think that was the name of our clan in the realm. I was always like one of those good guy people, which I think Horde is like the bad guys and Alliance is the good guys. I was always like a paladin and stuff, so that lasts a little bit. RuneScape devoured my life from ages 5 to 9. Yeah, I watched a guy, Brutal Moose. He plays RuneScape. He was really big into it. I think I just missed that by like 4 or 5 years. Classic Clans, people loving that. Druid High Life, Elf Baby. I say I don't even know. I don't know WoW well enough. RuneScape. Yeah, you guys, RuneScape was huge. Uh-oh, Brian's breathing in deep. We've had our 5 minutes. It's time to get serious here. We start off. Do play Roblox. I'm all about Joseph. Joseph, you got me laughing. You know what Joseph got? We got to hop over here. Joseph got some. Oh no, I don't have it. Oh, I do have it ready to go. I got it. Joseph got some. Joseph's the first person today to get some mega extra credit. That means Joseph got how many points? I want to see it in the chat. Remember, by chatting right now, we just have a little bit of fun at class to start. I have to go back to the main screen. I don't have the button on both screens. So let's go back to the lecture screen back here. Oh, Mega Mondays is still going. Go away, Mega Man. I forgot to turn off the Mega Man. But I don't have that button on both. I could put it on both things. I just have to put another button on my control panel. But I can't do the thing here. I could still say it, but I can't press the cool button. And cool button's still playing. If I went back to that screen, the buttons don't turn off. I have to press it once and then press it again once it's done. So yeah, remember those things. You love the Mega Man. That's awesome. Thank you so much. That was my favorite one when I found that gif of him just like rocking out. I thought that was the coolest thing. And it's also some symphony music of playing one of my favorite Mega Man songs. I've played it like 10 times now. I'm probably going to get like copyright ID. Yeah, this lecture's going to be hard. That's why we're going to get serious here. Brian's going to breathe in deep again now. Compose his thoughts and get ready right here. Here we go. Now, I want to say this. Remember, at the start of class, we always kind of understand what is going on with the world. Now, don't obviously miss the start of class. It's kind of like, hey, what's going on with the world today? So don't be like, I'll show up 10 minutes late. It's to let you know, like, today's Mega Monday. Here's the important things we have going on. And we're also going to have another note-taking quiz today. So if you jumped in right now, and I'm going to try to make sure this is in the video, or like the timestamp, you would need to know that also we are going to have a note-taking quiz probably due Tuesday night. Now, of course, the note-taking quizzes should not take too long. They are due when they are due. Sorry, I should have put it so it can't be submitted. Sorry if someone submitted it afterwards. Probably due Tuesday. Great question right there. There we go. And I agree with Isaac a little bit. It's very straightforward, I would say, but it's something a lot of people have never seen. So what is going on right here? We've got right here standard deviation is going to be used as a ruler for the normal model. So this really breaks down. Glad you guys like those note-taking quizzes. 11:59 buttons, 11:59 they'll be due. I would suggest doing them during class, but then I would turn them in. I'd turn them in right after class. I will be dropping 2 of them, so if you missed the first one, it's all right. So let's look at this right here. I'm going to add a green pen in so we can do a little more. So if you notice this right here, these standard deviations are this right here. These are the standard deviations. These are the standard deviations. And we also have, let's add in a highlighter. We have right here the normal model. Oh no, it's like 2 colors now. So we need to erase that. I like to visually show everyone what is going on right here. And so they're going to be similar. I think My Pearson, now don't freak out. If you have no idea what's going on with the My Pearson problems, the test is going to be really tough. The tests are going to be really tough. So if you're like, these My Pearson problems are impossible, but we're going to do a lot of them today. Now, don't think because you can do the My Pearson problems, you're going to ace the test. I mean, it's a good sign, but it's not like, yay, I did all the My Pearson problems. I can ace the test. It means you're going to do better on the test. Doesn't mean you're going to ace it. Remember, you do get multiple attempts at the My Pearson problems. You only get 1 attempt at the test. It's probably one of the most important things I can say is that just because you ace a My Pearson assignment doesn't mean you understand the material thoroughly. I mean, in that moment, you probably do. Yeah, and they are very picky. Please email me. Has anyone emailed me with a My Pearson problem that was too picky? I want to see some yeses in the chat. If you emailed me with a My Pearson problem that was too picky, and then I corrected it for you. We've got a yes right there. We got a yes right there. Please email me if you think one is too picky. And take a screenshot of it. Remember how to do the screenshots? Command-Shift-4 or snipping tool. Please email me if you think it was too mean. Now, I will be fair. Sometimes I'm like, that one was not too mean. But please email me if one is too mean. If you're off by like a lot, I'll be like, no, you need to get closer. So please email me. Yeah, so don't be too nervous about well, here's the biggest thing. Once again, I got to reiterate this. If you're nervous about the exam, remember, probably the lowest grades we see. Thank you so much, buttons right there. Probably some of the lowest grades we see on the exam are probably like a 40. Now, I'm not saying you want to make a 40, but that's like the lowest I've seen from anyone who said I've seen 20s, but the lowest I've seen from someone who said like, Brian, I'm just not being able to do well in the exam is 40. But if you do all the quizzes, which please, please, please do, you will make a 70. And we still have the drops in. A lot of people haven't used all their drops yet, but remember, we made a pathway to a B. Now, I'm not saying you want to make a B. I'm not saying like, yay, B, but I mean, if you made a B in Stats 1, because I know Stats is not everybody's forte. I love Stats. I love business analytics. But if you came out of here with a B, I think some people would be like, whew, made a B in Stats. Got a B in Stats. You'd be hyped with that B. There you go. So here's what is the pathway to the B. Do all the quizzes. Do all the quizzes. And you get 2 drops right there. You're right, Gracie. You got it. So please remember and start early. Like Alyssa's saying, if you want to make sure you get that B, make sure you're doing all of your quizzes. Do them right after class. Email me when you're stuck. Remember, I will email you back. Stat201 dash your Stat201 mini dash your initials dash title. I'll remind you in the bottom of the email if you don't. It really helps me reply to them quickly. I am going to Kingsport after class today, so I might be a little slow to respond. I have to do a follow-up doctor's appointment for my oral surgery that I had. How many quizzes do we get dropped? 2 for this section. 2 for this section. Please remember to do the quizzes. I sometimes send out reminders, so please remember to do the quizzes. Okay, let's do the easy part of the lecture. You ready? I'm going to erase this, then I'll try to remember that this is where the timestamp is out there. Alyssa, you know what? Alyssa, you get some mega extra credit too. Alyssa's helping remind people of a very important thing. Alyssa got some 50 points, mega extra credit. Sometimes it's a surprise, but I really like that mega right there. I can't hit the button. I'm on the wrong screen. Let's go. Nice job, Alyssa. Maybe you can only get the mega once, and I'm going to do it more randomly and throughout lecture, but keep it up. I would recommend taking notes every day, doing all of the quizzes, and then the night before the exam, go through your notes and study. The exam is planned for Thursday. I'm 90% certain. I don't want to say 99. But I was looking at the schedule of time, and we should have more than enough time to get to the exam by Thursday. Box. Don't worry, the whole exam is not box plots. I probably went more in depth than we should go on them. Like I like going into greater detail. That way, if you understand the high detail, you understand it well. Does the final replace if it's higher? The final is just the final, and it's averaged with the quizzes. I hope that, Mona, ask more detail if you want. Is there a certain time that we need to log on for the exam? 24 hours. You have 24 hours. Hey, Andrew, good to see you. We got some cool, fun new stuff, Andrew. You hang around. Check it out. He's going to be in 474, I think. Great student. But don't forget, we have class on test days. Yes, very important. And we will cover new material because it's 3 hours. When is the exam? Looks to be on Thursday. Is the exam on Canvas? Yes, the exam will be on Canvas. One project. The project will be due the weekend before the final. Is there a study guide? Yes, study guides are posted to stat201.utk.edu. A mod should be able to put in the chat. A mod throw in the chat. First person to put stat201.utk.edu in the chat, but it has to be a link you can click. First person to put it gets mega extra credit. First person to put it gets mega extra credit. We got to show Andrew that. Let's hop over to that full screen and show Andrew that credit. Who's going to get it? Oh, wait. It's got to be a clickable link. It's got to be clickable. None of these are clickable. None of these are clickable. None of these are clickable. Oh, wait. Oh, that's a YouTube channel. That's the YouTube channel, Claire. Wait. Nadai got it. Nadai got the mega extra. Wait, Needy got the mega. Sorry about that. Needy, right? Needy got the mega extra credit right there. Great job. Needy right there got the mega extra credit. Great job. Excellent work. Let's hop back here. Clickable link right there. People got it. That's the YouTube channel, which you guys are currently on. But then also, I know, right? So great work. Like I said, clickable link. So that way people know where to go. That's where post the files. So good job. Good job playing along. So I like doing stuff like that on Mega Mondays. I gotta slow down. I'm giving away so much mega extra credit. It's fine. Okay. Are you guys ready? We're gonna take another deep breath. I always want to answer all questions. I don't want people to have a question and then get stuck because you might forget it. I'm ADD too. Well, you might not be, but I literally am. But I always want you guys to have all your questions answered. And so at a moment like this, these are definitely great times to ask questions because once I'm on this slide, I can stop for a moment. Let's get started here. You got it. We understand what's going on with this chapter. We've got the standard deviation. Will you tell us when to begin the project? Yep. Yeah. Definitely, Neeland, you got it. I'll be like, the project is out, and I'll give lots of help for it. The standard deviation as a ruler in the normal model is so very important. Andrew, if you're still in the chat, do you remember using the normal model at all in 320? Z-scores, T-scores, anything like that? He's going to say yes. So we have the standard deviation to standardize values. The standard deviation, obviously, I'm reading a slide. Don't put that in the review. But the standard deviation is used to standardize values. And with this right here, we've got some people's heights. This is a little bit of review from the end of last class. And we have here that guys' heights have a mean of 69 inches. Oh, no, sorry to hear that, Andrew. 69 inches, and girls' heights have a mean of 63.5 inches, with a standard deviation for guys of 3 and a standard deviation for girls of 2.5. Now, this is probably one of my biggest pet peeves. It's all right, don't worry, I'm not that peeved. But people often don't understand what a standard deviation is. I think we understand what the mean is. It's the average of all the values. But the standard deviation is a measure of what? The standard deviation is a measure of what? The standard deviation is a measure of what? Remember, even if you don't get the mega, you still get points for talking and being here. It's a measure of spread, you're right. So everyone's saying spread, you're very accurate, because this tells us that guys have more variation in their heights than girls. Now, it's not saying like a girl can't be really tall or there's not variation within girls' heights. It's just that guys have more variation. Okay, so I want you to think about this question. What do you think has more variation in the amount of candy in the container? A bag, or let's say this, a fun-sized bag of M&Ms or a big box of Nerds? We're going to say a big box of Nerds, like one of the big ones you buy. Which of those would have more variation in them? So would a fun-sized bag of M&Ms, the big box of Nerds, would have more variation in them? Does that make sense what standard deviation is talking about? That the big box of Nerds would have more variation in them. And what do we mean by variation? It means that maybe the big box of Nerds might have on average, let's say like literally if you counted every nerd, because you got too much time on your hands. It's quarantine after all, so, he's like, I'm going to count all the nerds in a box. So the nerds, here we go, Mona, might have on average, let's say 2,000 nerds inside of it, 2,000 nerds. Then when you look at it, it would have a standard deviation right here of maybe like 100 nerds or something like that. Does that make sense? Like sorry, this is very hard to write this small, especially with my horrid handwriting. I'm trying to go up by 100, up and down by 100. But when you think about the little tiny bags of M&Ms, they might have variation in them like, okay, they might have 8 in them. And can anyone tell me what the standard deviation here might be? Not always, Jared. Jared, great question. Jared, amazing question. I'm going to put more mega out there. Man, I don't want to. Jared, you got mega. Why not? That's such a great question. Do you have an official definition of standard deviation? Because spread, I think I understand, but I want standard deviation is how far, this is going to sound so samey, but standard deviation is a standardized metric of something's distance from the mean. And so people are saying 2. I think 2 is too large. I think 2, everyone's saying 2. And I'll tell you why. Because this would be 6, this would be 4, and this would be 2. So I'm not going to say 2. You could even say things like 1.5. You could say that. It could be 1.5, or I'm going to go with 1 to make our life easier. It doesn't always have to be 1. But this right here is the variation within, thank you, Sarah, great question. This right here is the variation within a bag of M&Ms. Now, It's probably true that for things that have a lower mean, they have less variation in them, but that doesn't have to hold true. And Josh, this is kind of a great question, Josh. This is kind of theoretical right here. Imagine this. I want you to think about how many yards somebody gets in the NFL. I want you to think about how many yards someone gets in the NFL. How many yards might be the average amount of yards a running back, we got to specify position. How many yards might a running back get in the NFL? What would be an average amount? And people got to help me out here because I'm not. I'm not this. I'm not. Didn't wear my sports shirt today. In a season, in a full season, 1,000. 1,000 is such a nice number. So let's go with 1,000. Now this is hopefully going to be the average. Hopefully people aren't saying in the chat like that's way too much. Now we want to look at the variation in this. Roughly, I'm going to go with 900. And this right here is the average. I like 900 a little bit better. And now I'm going to give you 3 values. And I want you to tell me which of these 3 values you think would be the standard deviation. You ready? Here we go. Let's go with 5. Let's go with 1, 10, or 100. Let's go with 1, 10, or 100. I don't know. Sorry, I did that number. I'd probably go with 100 because that means if we go right here, we go down 100, we go down 100, and we go down 100. And maybe these are for, we could look at starting running backs who play a whole season. We might have to specify that these are starting running backs who play a whole season. And we're going to see this very shortly right here, that this would equate to 68% of the running backs are expected to get between 800 and 1,000. So that's the middle 68% right here. Hey, good to see you, Tracy. Tracy will tell you this is very important for the rest of the class. We're already on standard deviation, Tracy. So good to see you. That's the middle 95%. Tracy, for some mega extra credit, Tracy, within plus or minus 3 standard deviations, what percent of the data is within plus or minus 3 standard deviations? What percent of the data is within plus or minus 3 standard deviations? What is Brian going to try to scribble above this right here? What percent? Oh my gosh, people are getting the chat. Nice job. So right there. Oh my gosh, you guys know it. Justin was the first person to put it, and he beat Tracy right there. So 99.7. Thank you guys for putting in the chat. It shows you're following along. It shows you actually know something ahead of it. So Justin got some mega extra credit right there. These numbers right here are super important. 68, 95, 99.7. And the thing is, if I go back to my M&M example, which I was doing just a moment ago, all I'm going to do right here is change the numbers from 8. Okay, we're going to do one more mega extra credit. I got to calm down on these. Okay, remember it's Monday. Quick question. So was it that 2 wouldn't work? It wasn't. It could work. We could do it, but it doesn't make sense because then we're saying 68% of running backs should receive between 898 yards to 902 yards. So you would say, just so you can see it visually right here, and I'm going to ask a big question in 1 second. But if we did use 2, then we would say 68% of running backs are expected to receive between, do you see the 2 values right here? Let me highlight them. This is what 68% of running backs are expected to get between. So it doesn't really make sense logically. We're not actually, Justin, amazing job. Justin, if you don't have mega, you're getting it because I really appreciate those answers. Like, you guys are thinking through this. When you put an answer like that, you're thinking through it. You're helping your classmates think through it. And that's what this class is all about. Thank you so much, Justin. And thank you, Mona, for asking. Have we given Mona mega extra credit yet? Mona, you got mega. I gotta calm down. Okay. So here's the one I'm asking. Think about what Brian just said. Use the 68, and the first person to write in the chat, remember you do get points for just writing stuff in the chat. You get your regular extra for that. Was it 8? I think I put 8 at the center. Oh, well, darn. Now it's 9. Now the mean is 9. So can anyone tell me what the 68% represents right here? Let's see what people say about. So, but what does it mean? I need a full sentence. I need like the context of it. So keep going. Who's going to get it? I'm going to read off the answer when it appears. People are kind of saying it. I want to see I want to see full context. Not quite Q1 and Q3 because Q1 and Q3 would be 50% in the middle. The IQR, people are kind of getting. I'm not seeing the answer I want to see so far. The IQR would actually be within here. because it has to be even closer than the middle 68%. So the IQR would be in a little bit further than that. 68% of bags are between, I'll take that right there. Michael, I'll take that. That's a great answer right there. 68%, I would say 68% of bags are expected to contain between 8 to 10 M&Ms. So Michael, amazing job. Got some mega extra credit right there. And thank you everyone else for answering. Remember, you do get your regular extra credit for answering. So keep answering. Even if you don't get mega today, you still get your regular extra credit for answering. All right, come down this one. Isn't the IQR Q3 minus Q1? You are correct. And so if you notice, the IQR would be the middle 50%, and the middle 50% would be inside of the middle 68. So the middle 50% would be in a little bit further. So that's the middle 68. But if you want the IQR, it would be the middle 50. Hey, Tyler, good to see you. So does this make sense right here, what we're visualizing? That we have the middle 68, and that is kind of what we would expect between 8 to 10 M&M. So we have to keep thinking about this. We have to keep thinking, what does this mean? Great job. So here's the tallest people in the world. We've got Sultan and we got Yao. And so it's still, her face just looks blurred to me for some reason. So Sultan and Yao, now these are nothing against them, but these are heights you don't really want to be. Because at this height, you can notice both of them have canes. Yao has a stick. The stick is probably taller than me. I mean, she's 8 feet tall. Yeah, it's probably about as tall as I am. Almost as tall, that stick she's holding. she could just put her hand on it. She actually feel really good. But yeah, you don't want to be that tall. Causes a lot of health issues. So many health issues. My favorite tall person was Angus McCaskill. When your name is Angus McCaskill, Google him, read about his story. But Angus McCaskill, it just sounds, yeah, she could just go to the court and be like, boop, just like, dunk. But yes, not the best. So with this in mind right here, we go to the famous questions. I know that'd be not fun. We go to the famous question, who is more unusual? Now, when we think about who is more unusual, we have to do a formula. But this formula makes complete sense. Yeah, Andre had a lot of health issues too. This formula right here is going to do two things. And get ready for some mega extra credit again. I'm going crazy today, but this is one of the hardest lectures, so I don't mind doing this. Understanding how to get the z-score formula is very important. All this top part of the equation is a what? All this top part of the equation is just a what? I want to see someone in the chat. I'm going to call out your name. What is the top part of that equation? What is it? What's going on with that? Kind of. I'll take a difference from Matthew right there. That's what I was looking for. All these answers are pretty great. The top part of the equation right here is mainly just a difference. What are we taking the difference of? We're seeing how far an observation, this is the observation, is from the mean. Okay, so guys, we're going to talk to guys here for a second. Guys, I want you to tell me, so we know that y bar, now I want you to make up an answer. We did this, we're making sure we do this. I want you to make up an answer to this, and I want you to tell me your top part. Now make up something. Don't tell me your real answer. But 50, then you'd be 119. You'd be the tallest. I like that right there, Devin. So you're almost 10 feet tall. You're 9 feet 11 inches tall, because your height is 119 inches. 20. My gosh, everyone here is ridiculously tall. That's 89 inches tall. So 14. Why is everyone giants? Everybody is. No. 4. I like that right there, Sarah. 4 would mean somebody was 73 inches tall. Does that make sense what these answers are? Oh, it's so good to see you. So good to see you, Caleb. Thank you for swinging by. They're cracking me up this morning. We got people saying 3. Okay, what does 3 mean? If someone's top part of the equations, are there any questions on the exam asking just for no, but definitions help us understand stuff. I mean, I can't promise there won't be, but definitions help us understand stuff. Like, what is this equation doing? If somebody's difference up here at the top was 3, then it's so good to see Caleb swing by. Thank you so much, Caleb. I love seeing the difference between observation and the mean. Amazing answer. Gracie, you get some mega extra credit. It's just the difference between someone being 72 inches and then we have a mean of what we expect of 3. So this difference right here would be just we observe them at 72 inches, like somebody is 72 inches tall. And you got it, Isaac. We're going to tell you exactly what that means. So the very bottom of the equation right here, good question. This right here is the what. First person who tells Isaac gets mega extra credit. First person who tells Isaac gets mega extra credit. Maybe he asks because he knows. He's like, I'm going to get some mega. Kind of. I'll take that right there from Devin. Devin, you were the first, but be specific. First person to be specific also gets mega extra credit. Sample standard deviation. Kate said it in full. Kate, nice job. Kate is right. This is sample standard. I know I'm abbreviating, and some people did, and I give it to Kate because she wrote it out in full. But still, remember, there'll be more opportunities. Keep playing along. Don't worry. It's just practice. Right now, it's practice. It's not real till it gets to the exam. So this is sample standard deviation. So I want you guys to think about this. So you guys, because I'm from New York. So I want you to think about this. We're taking the difference between someone's height and the mean, and then we're going to divide it. You are correct, Isaac. That's how that one would be calculated. And so we are taking it and we're dividing by the standard deviation. So what are we doing? If Tracy's still here, she'll know this. What are we doing to the difference in their height? We are whatting that value. First person in the chat who tells me fully what it is gets the mega extra credit. I'm going crazy with mega today. Why not? Kind of. We're taking the difference and whatting it. We're taking the difference in their height, and I've given a hint. Because this is what this will be right here. Not yet. I might have to say it. Morgan, I'm going to take Morgan's answer because that's pretty much it. And Natalie. Morgan and Natalie got it. Morgan and Natalie got it. We are standardizing it because that's what the standard deviation does, is it's going to put it on like a scale. Remember the start of the lecture? It says that we are using the standard deviation to standardize values. So we are going to use the standard deviation here to standardize these differences. Does that make sense? Because think, this person right here, I want you to tell me, if the standard deviation is 3, somebody who is 72 inches tall, where the mean is 69, what is their z-score now? What is this person's z-score? So you can see all the numbers that would go into the equation. This person's z-score would be 1. And what does that mean in context? That means that they are what? First person who write a full answer here gets the mega extra credit. Remember, need a full answer. This person with a z-score of 1, what does that mean for their height? They are what? If I say my z-score is 1, that tells you something instant. Devin's so close. You've already got mega though, so you're good. People are saying away. No, wait. There we go. Thomas got it. Thomas, amazing job. I think Thomas was the first person to say 1 standard deviation above the mean. Because what if somebody's z-score, I got to make sure I scroll down. What if somebody's z-score was -1? What if somebody's z-score was -1? So what if somebody's z-score here is -1? That would mean, people are probably saying in the chat as I rewrite this right here, you guys are so awesome. Keep up the amazing work. I tell people about all the activity we have, and they're like, wait, how do you get your class to talk online? I'm like, extra credit. And they're like, it works? I'm like, it works. I'll tell other teachers, start giving them extra credit. Talk is how we learn. So when we look at a z-score, you guys are right. It's 1 standard deviation below the mean, because now this solves out to -1. So amazing job. You're right. And so it is true that they're 1 away. I mean, that is true, but thank you, Alyssa. It is true that they are 1 standard deviation away, but I mean, what if I told you my test score was 3 standard deviations away from the mean? What would you want to know? That means, so if the z-score is positive, then it's always above the mean. Camden, you're getting some mega. That's an amazing note that Camden just put in the chat. Any z-score that is positive is always above the mean. Camden, amazing question, amazing note. You're cluing in on it. So if it's 1 standard deviation away, would that 1 standard deviation below would be the 16th percentile, and I'll show you more on that in a moment. So, yep, good or bad. Kyle and everyone's right saying that, because if I'm 3 standard deviations away from the mean, either I scored somewhere on up here on the distribution of test scores. Now, these are not test scores, or I scored somewhere down here. So you can look like this means I did either really good. These are not test scores here, but just pretending, or I did really bad. So one of those two things happened if I'm 3 standard deviations away. Well, I feel like I speak for everyone when I say it's. Aw, thank you, Jared. You guys are awesome. I love it. So you guys know I love this. So there's the line. Woo! Fun. Here's where we're figuring out who is, and we did this a little bit Friday. Please ask if you're stuck on anything. I will try to answer every question. When we go right there, yeah, it does go fast. Positive equals above the mean, negative equals below the mean. You're right. And 0 means it's right on the mean. 0 means it's right on the mean. 0 means completely on the mean. That's what we get with a z-score of 0. It's an observation that is on the mean. So if someone said my z-score was 0, it means they got the average. You got it, Claire. Amazing job. Trying to it does 35 minutes have already gone by. Wow. What we get right here is if you look, Sultan's height was 99 inches. First person in the chat to tell me Sultan's z-score gets mega extra credit. First person in the chat to tell me Sultan's z-score gets mega extra credit. Sultan, you are right. Kyle got it right there. Kyle, amazing work. Kyle is correct. I'm going to write out the formula right here. We observe that Sultan's height is 99. That is the y. And then we know that Sultan's mean for the height of guys is 69. And then we have a standard deviation of 3. This makes it that Sultan is 10 standard deviations above the mean. The good news is remember, the first part, great question right there. I think Claire asked it. All we're doing right here is finding the difference between somebody's height and nice job, Morgan, everyone. Will we have to solve for the standard? No, never. I did such a waste of time, in my opinion. We'll use calculators and stuff like that to get standard deviations, and we really don't ask that much on the test because it does it for you instantaneously. So it's Sultan's y minus the mean. Yep, there you go. You got it. You're seeing it. Great job, Camden, right there. So all we're doing is taking Sultan's height. Let's highlight these things as we say them. Here's Sultan's height. That is how tall Sultan is. Here's the mean for Sultan's group. And then here, sample mean for Sultan's group. And here's the sample standard deviation. This is sample mean. This is sample standard deviation. And this is observed value. And then z-score is the standardized difference. I know, that is crazy tall. This is the standardized difference. Now, when we go and do Yao, who can tell me what Yao's first person gets mega extra credit? Who can tell me what? I could just erase it. Someone's already said it probably. Well, you guys are ready, Skylar. You guys knew that was coming. If I didn't say it, people would have been like, Brian, I was ready for that. Okay. So let's do this right here. So what do we need? We need Yao's height. Yao is 92 inches tall. And then, great job. We begin the, yes, great question right there, Gracie. Gracie, I'm giving Gracie mega. Gracie's asked a ton of great questions today. Not that other people haven't, but I've seen a lot of questions from Gracie. Gracie, keep it up. Keep asking those questions. Keep whenever you're thinking of something. Yes, great job, Isaac. Definitely remember that. So they're both highly above the mean, but what does this mean? Well, when we go back to our interpretation again, I think there was an additional question. Let me scroll up a tiny bit, because I'm going to answer Gracie's right here. When we interpret Yao's z-score, we can see that Yao is more unusual. She is shorter than Sultan. So Yao is shorter than Sultan, but she is more unusual in her standardized difference. I would just say she's more unusually tall. If I were to talk to someone, I would say for women, Yao is more unusually tall than Sultan is for men. Sultan is still the tallest man, but Yao is more standard deviations away. She's 11.4 standard deviations away, where Sultan was only 10. Only 10. That's ridiculous. I wouldn't say only. I would say Sultan was 10 standard deviations above the mean, which is ridiculous, but Yao is even more ridiculous at 11.4, which means she's more standardized metrics away. And think about this. Why would we ever standardize? Let me stay on Grace. I'm gonna answer Grace's question before I forget. Will we ever be given Z and then have to solve for another variable? You could. And an example of this would be Brian's height. I'm totally giving away my height right here. Brian's height is a Z-score of 2. Now, I'm going to write the formula for this, but I want for people to solve what Brian's height is. What is Brian's height in inches? Brian's height is a z-score of 2. And then I'm going to try to write the formula for it right here for those who need to know it. Brian's height is a z-score of 2. I wish it was grades too. 75 inches tall, you are right, Neeland. So, but think about when you hear it, so you got a nice job. When you hear 70, and Neeland, you got mega. I think I already gave it to you. I gotta calm down. But 75, when I say my z-score is 2, what should you hear in your head? When I say my z-score is 2, I want you to write this down. Brian's height is 2 standard deviations above the mean. Does that make sense? When you hear a z-score of 2, don't start thinking about a formula. Don't start being like, how do I solve this? Just think in your head, Brian is 2 standard deviations above the mean. Well, what's a standard deviation? It's 3, okay? 69 is the mean, 72, 75. So I try not to think about a formula when I do it. I just think about what a z-score is. It's how many standard deviations something is above or below the mean. So try this example. You ready? The average for the Stats 1 test was an 80. The standard deviation was 10. It was normally distributed. I'm teaching something new right now. So this right here stands for normally distributed with a mean and a certain standard deviation. You're super excited because your z-score was 2. You're super excited because your z-score was 2. What did you score? You're really excited because your z-score, you got it, Sarah. Nice job. Sarah, mega extra credit. You were first right there. I gotta calm down. Having fun here. So you're right. You got it. You know what's going on. You got 100. Now someone's really sad. They got a z-score of negative 1.5. Someone's really sad because they got a z-score of negative 1.5. Who's first on this one? Got a z-score of negative 1.5. 65, Skylar. We already give Skylar, but William got it too. Mary, you can only get mega one time. You can only get mega one time. Maybe Friday Frenzy, I'll give it. We'll do it twice, like Frenzy Friday, because I have to give more on Frenzy Friday. Or I might change it to 10 and just go crazy with it, and then just give it. You can go up to 50 or something. We'll figure out. We're always changing the rules, so stay tuned, stay active. You are right. If someone has a z-score of negative 1.5, they are 1.5 standard deviations below the mean. And so, Gracie, with the great questions again, please ask them all. Once again, I don't want anyone to please ask the questions. So the big N right here stands for normally distributed. That means if we were to draw this out, it would look like the following. So that's what that relates to right there. It means we do it with a normal model. Definitely email me. Yep, make sure. Email to us and everything. Can you say how that is calculated again? Sorry. No, great question right there. And then this right here stands for the mean. That value right there is the mean. And this value right here is the standard deviation. So if you were to use this information right here, first person, I want someone to write this right here for men in this format. First person, I want you to write it in this format. I want you to do the format Brian just did. First person gets the mega. I want you to write it in this format. I want you to write in the format I just did. I'm not going to write till someone writes in the chat. So who can write the notation I just did in the format? You got it, Nayland. Amazing work. So buttons, I think Nayland and buttons Nayland already had it, but buttons too. Please keep answering. And at the end, we might start allowing you guys to give others your mega. You can tag people. Not yet. But so 69 is the mean. And then 3 is the standard deviation. So we might start allowing people to give their mega to people who don't have it yet if you stay in the chat and stay active. So that is the notation right there where the mean is the first number and the standard deviation is the second number. And then people were wondering, how did we figure out, like if I said my z-score is 2, buttons, you got it. Neelan and Button got it that time. So you got it. So when Brian said his z-score was 2, I want you to slow your mind down. We slow down at times. We've been going pretty quick for a moment. That means when Brian's z-score is 2, Brian's height is 2 standard deviations above the mean. So I want you to think to yourself, a standard deviation is 3. And that means we just go above the mean 2 standard deviations. So it'd be 69 is the mean, 72, 75. Now, what we can do is, since we're given the z-score, and I hate solving the math on this. It's too much work to do the mathematics. It's easier to think it through logically. If you were to take and you were to go z times s equals y minus y bar, and then we are given z-score. Okay, then we want to find the observation. Yes. So y bar plus, because we're going to put it on this side of it. There we go. So I want someone to put, I'm going to highlight the formula, and my brain just slowed down. There we go. I want someone to fill in the numbers in this formula right here. I want someone to fill in the numbers in this formula. You get mega. Fill in the numbers in the way I've rewritten this formula. You have to fill in the numbers right here, which will solve. You have to fill in every single number so people can see it in the chat. But remember the question. Brian is 2 standard deviations above the mean. You're given all the information right here also. For men, that is correct. Yep. Brian is 2 standard deviations above the mean. Fill in all the information. Fill in. There we go. Jared, amazing work, Jared. Jared got it right there. Nice job, Jared. So you are correct. So you see what's going on. You can see 69 is the mean for, so you're practicing right now if you can't tell. By doing this, you should understand that this is the mean for guys' heights. This is the z-score, which is how many standard deviations Brian is away. Look what it's connected to. It's connected to standard deviations. Like literally, we are literally adding to the mean how many standard deviations an observation is above or below it. So when you look at this right here, it's the mean, and then we add to it the amount of standard deviations that this observation will be above or below it. So it's how many standard deviations something is above or below the mean. So I think the definitions can really help you understand the concepts rather than just solving the mathematics. So whenever someone says to me, oh, my z-score was 3, I'll be like, oh, you're 3 standard deviations above the mean. And then I could just know what the standard deviation is and then add that to the mean. So I think we got that right here. We're good to go. You could do the thing where you just say, well, what if someone has a z-score of 0? You'll see right here, if someone has a z-score of 0, then this would go away because you would times that by 0, and then someone's observation is the mean. Let me go ahead. I want to make sure these things that I keep on here, because I do post the annotated notes. Thanks for those who want them, and I should be able to do that right after class too. Good question, Jack. A z-score is how many standard deviations an observation is above or below the mean. A z-score is how many standard deviations an observation is above or below the mean. Thank you so much, Kyle. So if your z-score was negative, then would you subtract? Kind of. I mean, it would do it itself. If the z-score is negative, you wouldn't really subtract. It would turn the whole thing negative because you're gonna multiply this out. So you would still add it. I know it just sounds weird, but you are going to then, it's going to make that negative. You're still using the same formula, but then that would be negative. So it is how many above or below. So when it's negative, the plus becomes a minus. Yeah. You're adding a negative, which is, yeah, it's just the way it mathematically works, that you always solve it with this, but when the z-score is negative, then you're adding a negative, like to be kind of exact with mathematics. Great questions. Keep asking them because, I mean, it's how we learn. See you guys making, yeah, you're welcome, Jack. Great questions. And I really mean that. Like, this is, I get to pause for a moment here. I get to breathe. But y equals y bar. Oh, the equation we just wrote. So the equation we just wrote is if someone gives you a z-score, you can use this to solve. I mean, they could give you, stop squeaking. Would you ever get a negative number? Yeah. There's a lot of times that either the observation, the mean, or the standard deviation can't be negative, but everything but standard deviation could be negative right here. Button's got it right there. So everything but standard deviation can be negative because that would be like saying something has negative spread. Spread is how the smallest spread you can have is 0. 0 means no spread. Like the distribution would be like that. There's no spread to the distribution. But the bigger the spread, the more spread out it is. I mean, I hate to use the same word, but the bigger the spread, the further out the values go on the number line. Great job right there, Kyle, helping me out right there. So smaller standard deviation means it's in closer to the mean. Larger standard deviation means it's further out from the mean. So that's the value of S can't be negative. Y bar can be negative. That would just mean the mean was negative. Like if you said like, maybe it's like values of money, and you're looking at how you do at the stock market, negative would probably mean you lost money. Like what is the amount of money you make on the stock market daily? So if Z was negative, that would mean you're losing money on the stock market. If you had a z-score that was negative, that means you did even worse. It means you were below the mean. And then the observation right here would be how much money you made or lost. So if it's negative, you can lose money on the stock market. So everything but the S can be negative in this. That's kind of a good theoretical question too. I might put that, I don't know. It's not going to be on the test, I don't think. Don't worry. Be like, which of those can be? It's just good to understand why S can't be negative. Got it, but obviously this would not be negative. Yeah, exactly. Great job, Claire. You guys are getting it. Yep. You can't have a negative height. You can't have a negative mean for height, but you can have a negative z-score because you can be below the mean of height. So, and then you can't have negative standard deviation at any point because standard deviation smallest can be 0. You guys are awesome. You guys are awesome in the chat. Okay, so guess what? With all this, we've done so much good work in understanding what we need to know next. What we need to know next is the idea of standardizing things into z-scores. So when we standardize things into z-scores, the relationship between z and s is very important here. Because the relationship between z and s is z literally tells us how many s's something is above or below y bar. This is kind of an easier definition maybe. Z literally tells us how many s's something is above or below y bar. So z and s are very connected because z is a standardized metric, which means it's in terms of standard deviations. Now, what we like to do is we like to shift everything to 0 and rescale it to 1. So when something has a z of 0, as we've been saying repeatedly, the mean is 0. And when something has a z of 1, it is just 1 standard deviation above the mean. When something has a z of 2, it's just 2 standard deviations above the mean. So z is used to tell us in terms of s. So we see right here, we do this all the time. You guys know this, that you can kind of, you'd be like, Brian, you can't just change the unit something is in. You do it all the time. We've got here 2 distributions. We've got the distribution of temperature in Fahrenheit and the distribution of temperature in Celsius. Now my friend says to me in Australia, he says, Brian, it was so cold today. It was 0 degrees Celsius. And I say, well, it was colder here in Knoxville. Today it was 32 degrees Fahrenheit. Where was it colder? Where it was 0 degrees Celsius or 32 degrees Fahrenheit? First person, mega extra credit. Who's got it? 32 Fahrenheit or 0 Celsius? Neither. I'll take that right there. Same, Ethan. There we go. Scholar's already got it, and Ethan's got it now. You got it. It would be the same thing because 32 degrees Fahrenheit is freezing in Fahrenheit, and 0 degrees Celsius is freezing in Celsius. They're kind of off the scale right here, but they would be down here, 32. Oh, you can't see it off the screen literally for you guys. They are off the screen. They're the same thing. So when someone says to you, like in our previous examples, Brian's height is 75 inches, Brian's z-score is 2, that's the same thing. Because all we're doing is converting it to a new standard. Does that make sense? If I say Brian's height is 75 inches, Brian's z-score is 2, that's the same idea as saying it's 32 degrees Fahrenheit, it's 0 degrees Celsius. It's changing the scale by which we measure things. So it's still a way to measure it. It's still saying you are this many standard deviations above or below, and we can still compare things. Like you would say, which day is colder? The day where it is -2 standard deviations below the mean, or the day where it's -2 standard deviations below the mean? Which day is colder? Who's got this one? First person, mega extra credit. So the day where it's -2 standard deviations below the mean, or the day where it's -2 standard deviations below the mean? Neither, Thomas, you got it, because I'm doing the same thing I just did a moment ago. But now I converted the temperature Brian observed and the temperature Cody observed to the same scale. So think about this. It doesn't matter if Cody tells me the temperature in Celsius if I convert it to a z-score. So what does z-score do? It's a unitless way to measure stuff. Does that make sense? You don't have to worry about the units. I guess you could say it's in units of standard deviations, but we think of a z-score as unitless, as though it doesn't have any like Celsius, Fahrenheit, inches. So would it be a good idea? Think about this. I have a friend who measures his height in meters. I have a friend who measures their height in centimeters. That'd be easy to convert though. And I have a friend who measures their height in yards. I have a friend who measures their height in feet. We could convert all those to what? Mega extra credit time. Who's got it? You could convert every single one of those heights into a what to compare them all. Kyle's got the point right there. Kyle. Mega if Kyle doesn't have. Kyle, you got mega. Z-scores, Hannah, you're right. Nice job. Hannah got some mega also. Remember, you can only get mega one time. I think we're going to change the rules for Friday where I can give it out more, so that way I can just go even crazier on Friday. But no, you guys are following it. If you converted everyone's height to z-scores, it wouldn't matter what units it was measured in. You wouldn't be like, well, this person was measured in meters where this person was measured in centimeters. Well, and you would have to convert each height depending on the metric that was used. But if you convert everyone's heights to z-scores and record them all as z-scores, then it doesn't matter what units it was taken in, as long as you do the conversion properly, because you have to convert it based on the units it was taken in. Normal models, is that really that whole section? I may have done these notes 1,000 times, maybe 50 times, but wow, that's short. So the normal model, what is the normal model? The normal model right here is that. The normal curve is unimodal and symmetric. By unimodal, we mean it has one mode right there. There's the one mode for the unimodal curve. For symmetric, we mean like when you fold it over, pretty normal right there. You got it. We've got this normal, unimodal, and symmetric. And so those are the two keywords you should always remember. Bell-shaped curve, you got it. So remember the two keywords, unimodal and symmetric. One time I tried to think of a way to draw it that it would be unimodal and symmetric, but not be normal. I'm waiting for a stats person. Can be like kurtosis. Yeah, okay, kurtosis. Sure. Well, that's uniform. Kurtosis. I never said that kurtosis word. Don't go googling it. It's not like it's a bad word, but don't worry about kurtosis. Wikipedia will help explain what kurtosis is. It's not in 201. That's the only thing you know. Kurtosis is not used in 201. So someone's gonna start typing in the chat explaining kurtosis. Even I don't understand kurtosis. Unimodal and symmetric equals the normal curve. You got it. And we can see here that these individuals have extremely, extremely crazy observations. And so here we are. Here's the normal model right here. You can see that as Brian was drawing out with his examples, we have the line here on the bottom, and you would go up 3 standard deviations. So I'm kind of doing a really squiggly 3 standard deviations, and let's see exactly. And you might be able to explain it better than I understand it, because I always call it peakedness, and then the Wikipedia will be like, often called peakedness, but not quite really peakedness. Kurtosis is a misunderstood concept in statistics. If you look at where Yao is at, and I probably didn't do all the standard deviations properly, Yao is way off the curve. So is Sultan. And I probably didn't do this justice because she's 11.4 standard deviations above the mean. So it's not peakedness, it's tailedness. I need to read more on this. And so, because, yeah, wait, I need to go back on topic. So what we see right here is Yao is ridiculously unusual. Now, what we should know is that when we do z-scores, here's a big note to take. We saw this earlier. Sarah, amazing note. Sarah is totally right. It's tailedness? Oh, I need to start saying that. Jared, you got mega extra credit. And Isaac, you guys are teaching me stuff. Great job. Figured out how to spell it too. So what we see right here is very important. Here's the big notes you need on this slide. You ready? Here's the big notes. Every time I say it's the big notes, you should have your pen out and make sure that you're writing down these big notes. The N right here stands for normally distributed. That means when you draw something out, you need to use this right here. The mu right there stands for, this stands for the mean of the curve. And then the sigma is the distance each of these standard deviations are above or below. That's sigma right there. And that is represented by this right here. And each of those are 1 sigma. So, nice job. So we have right here what each of these mean. The mean, which I did a pretty bad job of putting that at the very center of that curve, but the mean is mu. Mean is mu. And very specifically, someone might even wanted to correct me there. Mu is population mean. And let's draw these out while we talk about them. Mu is population mean, where y bar is sample mean. And I'll repeat right here again. And then sigma is population standard deviation, where S is sample standard deviation. So if you notice, I'm putting here the population parameter, and down below it, I'm putting the sample statistic. Population parameter, PP, sample statistic, SS. Once again, mu, sigma, would be the population standard deviation. And then S would be the sample standard deviation. And to repeat again what these things are, the N right there stands for normally distributed, which means we draw that bell-shaped curve right there. And then the mu is the very center of the curve because it's the mean for the population. And then the sigma stands for the standard deviation of the population, which is the spread. So think about this. If you were to make sigma smaller, then you would make that kind of distance smaller right there. So when you make it larger and smaller, my man. So does that make more sense? Do you guys have the notes on this? This is the big important thing. We see the z-score formula once again, which is just observation minus mean over standard deviation. Once again, as I say it, observation minus mean over standard deviation is standardizing the difference between them. Makes sense? Good stuff right here. So we have the normal model right here called the standard normal. And what do we mean by the standard normal? Where the mean on this is 0 and the standard deviation is 1. I want you to tell me every number Brian is putting on this curve is a what now? If the mean of this is 0 and the standard deviation is 1, on the standard normal curve, every number on it is a z-score. Buttons, great job. Who else? We need one more. Buttons already got it. So Keaton right there. Keaton's got, I don't know if we've given to Keaton yet, but Keaton, you've got mega extra credit. Every number down here is a z-score. Every single number right there is a z-score. Now, I do want to point something out that the curve does extend out even further, but it's just that there really aren't that many observations out that far. You can be off the curve. I mean, like off what we usually draw. There really is no off the curve because the curve is infinite. This curve actually does go negative, but that doesn't make sense. So it would actually have an area underneath it, but it's just because statistics aren't perfect. We're trying to use a model to explain people's heights. And I guess that's what gets me about, like, sorry, we don't want to talk about the world event that's going on, but people are like, the stats were wrong. I'm like, the stats are never perfect. I mean, they can be close. We're trying to use mathematical models to dictate reality, and no mathematical model, it's just you're trying to use math to predict the world or to explain the world. It's usually pretty good and it's somewhat accurate, and a lot of things are. Oh, and then models are so difficult for so many. Yeah, exactly. And that's the thing too, is there's so many inputs that it's like a very complex model. And then there's variation within each one of the inputs. But usually they're like, you can look at how close they are and it's like, they're kind of accurate to a certain degree. We have a very famous saying in statistics, all models are wrong, but some are useful. Every model is wrong because you're trying to use mathematics to explain the world. Okay, I want you to think. This model is wrong because it will eventually go to negative heights. Like, it will extend out. You can't really see it. But does this model look very, very useful? Get 100% correct. But all models are wrong. Some are useful. That's George Box, I believe. So, and actually, I've got a book signed by him. I should show you guys that. My dad's a statistician. And he met George Box in the 80s, like when he was my age. But all models are wrong. Some are useful is one of our very famous quotes in statistics. It's just because, yeah. And so I would say, Box Hunter, the guy right there. Oh, like Boxlot. And so I would say a lot of our models with the current world event are very useful, but they're still wrong. Am I smarter than my dad? Not in a lot of areas. My dad has a lot of skills I don't have. So I'm not trying to gloat like, I'm better than him at this. But yeah, and I agree with Isaac right there. My dad has so much woodworking skills that I'm so jealous of that. And he has so much like mechanical skills. Like my undergrad was psychology, and then I came back for a master's of science business analytics. And so one of these days maybe I'll have my dad appear on one of these streams. So maybe I'll call him up here or something, or but yeah, he knows his stats. And he worked at Eastman, Pepsi, Lipton, trying to think where else, but yeah, he knows his stats. Oh man, PhD is tough. 3 courses down, a lot more to go. Yeah, no, woodworking skills and stuff, sorry, is our little aside before we get to something huge here. We should have I know, it'd be so cool if he appeared like beside me right now. But like I wish I had his mechanical and woodworking skills. Like I wish. One last quick story. I was helping my dad cut down a tree in the yard with a chainsaw. My dad still climbs trees. He's 70 years old and he's still climbing trees in the backyard, like with his belt. I'm like, and so I'm in the backyard with my dad. This is about 10 years ago now, actually. And we got this tree, and he's putting the cut into the tree to like get it to fall. And I'm like, Dad, that tree's gonna fall on me. And he's like, it's not gonna fall on you, son. And I was like, he's gonna tell this story. I was like, Dad, the tree's gonna fall on me. He's like, no, just keep pulling. It's gonna fall this way. And I was like, no, Dad, the tree's gonna fall on me. He's like, just stay right there, son. I was like, no. He's like, it's gonna fall on the driveway if you don't pull it. And I was like, it's gonna fall on me. And I go inside and I'm complaining to my mom. I'm like, Dad's trying to kill me out there. He's trying to kill me. And so, and then my dad comes in, he's laughing. And he says, you're right. It fell right where you were standing. I was not happy. I was right. Oh, man. Oh, God. Oh, God. That's our fun for the moment right there. Now we got to get serious again. He just came in, he was laughing. We were in like this, not like, I mean, kind of like a shouting match. Because he's like, you need to pull the tree because it's going to hit the driveway. And he didn't want to mess up the driveway. And I was like, no, Dad, if I pull the tree, I'm really going to pull it on top of me. And yeah, we can talk about nulls and alternatives here. My null hypothesis was that it was going to fall on me. His null was going to hit the driveway. I feel like a lot of dads are like that. Yeah. Okay, here we go. You guys ready? Uh-oh. Brian's getting really serious right now because here comes a very, very, very difficult topic. This is probably one of the most important things we should know. 68, 95, 99.7. First person to put it in the chat. We're getting back on topic right now. First person put 68, 95, 99.7. You know what's going to happen. 68, 95, 99.7. Maya right there. Amazing job, Maya. We're back on track right now. We had our 2-minute break. 68, 95, 99.7 is the empirical rule. What do these numbers mean? What does 68, 95, 99.7 mean? Well, 68, 95, 99.7 is the percent of area within 1, 2, or 3 standard deviations. Now, these numbers are super important. Let's go over here to a work screen. Oh, you know what I'm going to do? I'm going to speedrun this. Let's go to speedrun. We got all the Mega Mans. Oh, no, our timer's not up. I forgot to click the timer this morning. I think I adjusted it by accident when I was working with it yesterday. There's the timer. I got to move it to the other screen. Is it yet? When I was doing some work this weekend, I accidentally misclicked it. You didn't see that? Everything's perfect. There's the timer. Doing work this weekend. This is still population, correct? Yeah, generally we think of these as population, generally. And so what I'm going to do right here is I'm literally doing, I believe, your next note-taking quiz. So have your pen out. Be ready. This is your next note-taking quiz. I'm going to use the graphic because... Really? Where's my graphic? Got to go back to here. Did I not copy this? Can I not copy it? Copy. There we go. There's the graphic. It's going to be much easier to read if I use the graphic than if I don't use the graphic. Like, my handwriting's not the best. But if I use the graphic... It's going to make our lives a lot easier when you're trying to read this. So I get this as a start. All I needed to know for this was 68, 95, 99.7. As long as you guys trust me that Brian knew 68, 95, 99.7, then he understands it. I'm now going to solve for every single number under the curve. Like, I'm going to solve for all of these. Thank you so much. And we got all the pens back. Space Pen, where are you at? Space Pen is here. Space Pen is back. You know it. There's Space Pen. So we got all the pens, but I'm probably going to use more like black pens and stuff like that. Trust him, Brian. Thank you guys so much. So here are the numbers we got going on. You ready? We're going to find all of the numbers within these areas. As in, this area is the area between... I'm going to have you guys sign this one real quick before I speedrun it. Does X and Y look equal to each other? You guys are too much. Does the area between X and Y look equal? And what do you think they are equal to? I bet you guys can solve this one. Who knows what this is? Gets the mega. Who knows what this is? Gets the mega. What is the areas for X and Y? 34, Jared, you are right. Jared got it. So now we are ready to speedrun this. I'm going to slow it down after. So watch the speedrun, then we'll slow it down and do it again in a slow run. Here we go. So here we go. What we have right here is 68% of the area is contained within plus or minus 1 standard deviation around the mean. because this area is symmetric, as you can see as I trace over it, we can cut this area in half right here and get that each of these is worth 34 right here. Now we're going to do something really crazy, is we're going to talk about the inside-outside trick. Take a note right here. I'm slowing down for just a moment to tell you the inside-outside trick. The inside-outside trick works the following way. If 68% of the area is inside of here, what's outside of here? Well, 68% inside. That leaves 32% outside total. Now, I've got two things right here with two things. 32% divided in half is 16%. Does everyone see that right here? That means above 1 standard deviation is 16%, and below -1 standard deviation is 16%. Now we go right here, and let's go to -2 and +2. Now, within -2 and +2, as you can see, is 95%. I sound like someone doing an auction right now, but that's 95% within that area. But now we need to think about, if we're going to talk about outside of that area, what would be outside of this 95%? Outside of this 95% would be what? You should be saying in your head, 95% inside, 5% outside. Well, 5% is in 2 quadrants. Well, that would make the 5%. You should be saying it, 2.5%. We're just going to cut it in half right here. Here's the 2.5% right there. Last but not least, we go to the furthest one. You guys are doing a great job in the chat. You'll notice right here between this area is 99.7%. With 99.7% right here, what would be outside of it? It would be 0.3. With 0.3 outside of it, what do we have? We have 0.3 divided in half is 0.15. We were almost done here. We're going to be done in sub 2, I bet. You got this. Because if this is 0.15, we got this right here. And then we subtract off these 2 quadrants. Got to show what I'm doing. I'm going to take this and subtract it from this. This is 2.35. Oh, no. That's going to burn the speedrun right there. 2.35. Then we're going to do the same thing right here where we take this one and subtract from this one. Guess what we got right here? We're going to have 13.5. And we're going to do 13.5. I'm not going to go sub 2. 2.35. 0.15. Oh, we did it. No, I shouldn't have done that. I'll be right back. I gotta try the pen. No. I lost the pen. Oh, I got it. I shouldn't have thrown the pen. Oh, man. I broke the speed run. Okay. Mic drop. Okay. This is a horrible handwritten speed run. Okay, let's slow it down. I had a little too much fun there. Okay. I said I'd slow it down afterwards. Remember that. Okay. So I really scribbled the last bit, and I talked too much like someone trying to auction off stuff. But we had some fun right there. Okay, let's slow it down. Let's see how to do this. Okay, you ready? I know we went really too quick right there. All right, we need to do a slow run now. You ready? Here's slow run of it. I'll probably put in the notes speed run, then slow run. So what we're talking about, let me slow down here and let's answer. I'm going to answer a lot of questions as we do this right now. I'm trying to figure out the area that would be contained in these things right here. Does that make sense? Like if you were to talk about test scores, we said earlier that test scores could be something like this. Here's a very slow question. What is the standard deviation on this model right now? We're doing a slow run right now. This might take 10 minutes. What is the standard deviation on this model right now? 10. You got it. So standard deviation here is 10. And then this area right here would represent the amount of people we expect to score between a what and what. And then we would say we would expect blank percent of the class to score between these values. This is where I want you to understand like what exactly this means. So between 70 and you're right. And then what percent? You got it, 34. So when you solve for this number, this 34 right here, you'd be saying, I expect 34% of the class to score between a 70 and 80. Does that make sense? You're literally solving for this area right here, which is, you wonder, how did we get 34? Well, due to the rule of symmetry on the curve right here, this is 34 because it's half of 68. There's a lot of ways to solve for these numbers. I'm showing you probably my favorite way. You can also memorize 0.15, 2.35, 13.5, 34, and then you can write all the numbers. But double check your numbers too. I would expect Alyssa, amazing work, Alyssa and Keaton. I think you both have the mega. You definitely got it. We're not on the right screen for mega. I wish we were. But great job. I would expect 30% of the class to score between a 70 and 80. Exactly. What percent of the class do you expect to score between an 80 and a 90? What percent of the class do you expect, first person to say it gets the mega also, what percent of the class do you expect to score? You'd also expect 34. These right here are the z-scores. This is what I call the context of the problem. So you've got the z-scores and you've got the context right there. The number line right there is the z-scores, and the number line down below is kind of the context of the problem. To say someone has a z-score of -1 is the same thing on this curve as saying someone has a score of 70 on the test. So I always like to draw both of these together to give context for it. I started doing what I call the inside-outside trick. So I do what's called the inside-outside trick. And let's talk about that inside-outside trick. If we have, I want you, now slow down here. We're going very slow. This is the slow run. I've got 7.5 minutes to still get the slow run record. If 68% is inside of here, then what is total outside? I want the total. Be careful. I want the total outside. And I want us to think about how we got that number. Because sometimes people say, how'd you get that number? 32. 32 is total. Now, how are we getting that? We're subtracting it from 100. Because everything under the curve, like the whole curve, is 100%. So if we know 68% is inside here, then the remaining outside of there would be 32 because we're just subtracting from 100. So that's how I'm obtaining 32. But then why might the answer be 16? Nice job, Keaton, in the chat right there. 16 on either side. Morgan, you're right, because we're just dividing it in half. Amazing work. Morgan, I don't know if I've said your name today, but Morgan's got some mega extra credit right there. You are following along, and if you're giving the next answer, you know what's going on. You're being like, okay, I get it. Now you're going to say 16 is on either side. Amazing work. I see 16 is half of 32 in the chat. Nice job. Olivia, you got some mega too. That's a great explanation of it right there. We're just cutting it in half. So we're going to do the same sort of thing right here. So now we're going to go to 95, and it's a little bit harder to draw. I'm going to go to that number right here. What is outside total of 95? What is outside total of 95? You got it, Claire. Nice job. And then we're going to cut that in half. Now, when you're drawing this out, and you need to turn in a picture of this, if you're practicing and drawing this on, this is your next note-taking. Great job. You guys are getting so much extra credit today with Streamlabs and everything. What does the area add up to along this? What would this add up to? What do both of these add up to? What do the pink and the yellow highlighter add up to total when it comes? You got it, 100. Because these arrows extend across the whole curve. They don't, I'm saying they go out completely. So they cover 100% of the curve. No. And now we go to the next one. And this one right here, this goes, there is area outside of this. I want to make this very clear that there is area below -3 and +3. And you got it. Nice job. Jose, mega extra credit, first person to say it. You got it. This is 0.15 and 0.15. So now this is the easiest number to get right here. This first number just means below here is 0.15. And here's where people usually make a mistake. The mistake people usually make is when they try to figure out, let's do maybe an easier one to see. Let's try to figure out this area right in here. Does everyone see the area that I'm highlighting? Just for the moment, I want you to figure out the area right there. And how would you figure it out? You got it, Claire. And I want everyone to look at Claire's 13.5. Because she took the two arrows. She took this arrow and subtracted off this arrow. Because you don't want this full thing right here. We're going to have to space highlight it. So what did she do? If we call this, let's call this right here y. Oh, no. And this is x. She just wants, think about y minus x. What would that give you? Y minus x would give you that area right there. Does that hopefully visually make sense to people right there? Because you're taking the full thing and then cutting off this area right here. Hopefully that makes sense visually what's going on when we do the mathematics here. So, makes sense? Good. Hopefully, yeah, that's why I love that. This tablet, so awesome. So that's how we're getting that this area right here is 13.5. And due to the law of symmetry, this one, do you see how those things, let me highlight them. This right here looks just like this right here. It's the same thing. It's the same symmetric area. So we can just easily say that they're both 13.5. Now, and there's a lot of ways Kyle might, yes, Kyle, that is another way. You got some other ways, Kyle. That is a great way. Kyle, you got mega. You got it, Claire. Amazing job, Claire. Claire got the next one to see that here's the small arrow and here's the big arrow. And if you notice, and my arrows should go, just so you guys know, I want to make this very clear. They do go all the way out. Like they go out to like negative infinity. Just to be very clear, they don't. I hope no one thinks that I was trying to stop that arrow right there. That arrow goes all the way out. So what are we doing? We're taking and subtracting kind of the overlap. This is where the overlap is. So we're subtracting that off of the 2.5. Now, once we do this right here, and please, if you see anything you have questions on, this is a, and then this is 2.35. My handwriting's a little bit better this time. All of these numbers I've highlighted on the bottom now must add up to what? A 100. You got it. Yep. This should be 100% of the area right here contained on the curve, and that's what we got going on. It'd be 100%. So this would be 100% of the curve because it extends all the way out. So it'd be 100%. But I could do the following. All of the numbers highlighted right here should add up to what? If I add up those numbers, they should add up to what? Yep. They just go to infinity just because, and it's so little area. Sorry, Camden. I hope that's like a good enough explanation. They just extend out because it'd be the area below -3. There's 0.15, and people are saying 95. That's correct. So it's the area below -3 is 0.15% of the area. Very few observations are 3 standard deviations below the mean. So they go out to, it's just like, once again, it's not a perfect model. So sometimes it might not make sense that it goes to negative. Don't worry about that. Like, I wouldn't put that on the test. But the big thing, let me say the big thing to know about that, is that the curve has values below -3 and has values above +3. And those are considered outliers. Values outside of -3 and +3 are considered outliers. They are very unusual. But it's important to know that there are values outside of here. We really don't try to think that the curve conceptually does go to negative infinity, but I mean, that there's like the probabilities of those are infinitesimally small. Like winning the lottery every day for your life, small. Even smaller than that because it's negative infinity, like infinitesimally small. So, I'm going to give myself that speed run too. Been cool if the last one was 159.99. So with this normal model, can we just memorize? You can. Yes, Ben, that is correct. You can memorize. I usually do it the other way. I usually do it 0.15, 2.35, 13.5, 34. And then check your numbers. If you do write out those numbers, Ben, and you do memorize it, because I do have those memorized also. If you do memorize those numbers, double check them. 34 plus 34 should equal up to what? If you are checking those numbers after using them, 34 plus 34 should equal what? 34 plus 34 should equal 68. The 13.5 and through everything here should equal 95. Then everything here should equal 99.7. And all the numbers you use should equal 100. So you can literally see here, 68, 95, 99.7, and then everything's 100. So you should know, I would also remember 68, 95, 99.7. This leads to a lot of interesting stuff right here. And we'll be showing the rest of it in a moment. But this is a very, 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 very big topic. And we'll be using it a lot in the homework, which we'll be doing towards the end of class. So I am going to try to do the homeworks and quizzes in today's lecture. So, because I will stay a little bit through office hours, but then, like I said earlier, I have to go to Kingsport and see my parents. So wear my mask, see my parents. So Brian's got the high score on the quarantine. Going back. Did I do it? I did. There we go. We got our slow run. We got our speed run. So we know what's going on. Okay. So Z-scores. If it's outside of 3, it's an outlier. Big note right here. So notice that we say if it's outside of 3 in absolute value, that's an outlier. Someone can be unusually tall, unusually short, have an unusually high score, have an unusually low score. Outside of 3 just means they are more than 3 standard deviations above or below the mean. So you can be an unusually low observation, or you can be an unusually high observation. Either of those is possible. You'd be an outlier when you're outside of 3, and I will say this, it's not like when you achieve a z-score of 3, you are an outlier immediately. This is a big thing that I think people should realize, is that we live in a world of grays, as in, like, imagine somebody has a z-score for their height of 2.9. It might be an option. I can tell you that at the end, Claire. Go to, it's like properties, and you should be able to add it in. It's like a tab you have to add in. Like, Claire, Google this. So you can Google this in the background right here. Enable draw tab in PowerPoint. Do that right there. Enable draw tab in PowerPoint, and when you read on that, look on that, and that'll have you add the tabs. Can this be used for categorical and no? The normal model is a quantitative distribution. So everything we're doing right now, Camden, amazing question, is all based on quantitative data, because when we do this, we need numeric data. So these are all quantitative values. These are all quantitative. Great question, Camden. Everything today has been like height or test scores or amount of M&Ms in a bag or amount of nerds in a box. So those are all, or amount of running yards a running back receives. So it's all been quantitative. Camden, you've already got the mega, but that was a great question. This has all been quantitative models today. Bringing it back to the basics, which we like. So it's all quantitative today. Quantitative all day long. So, yes. What we have right here is that we need the data to be normal. And we will talk about this later in the semester, and people forget this. Now, later in the semester is like 2 weeks away for us. So we need to remember for 2 weeks from now what it means for data to be normal. If a z-score for height is 3, yep, that would be an outlier, Jared. Yep, that'd be an outlier. So, and then if it's like 2.9, it's pretty much an outlier. That's why I was saying it's like, it's not like a 3, it magically becomes an outlier. If someone had a z-score for their height of 2.9, I'd say, well, you're pretty much an outlier. If they were like 2.4, I'd say you're pretty high. If they're 1.8, I'd say you're a bit high. If they're 0.8, I'd say you're just a little bit above the mean. If you're 0, I'd say you're the mean. So it's not like a 3, it's magic and it becomes an outlier. But a lot of people use 3. It's like saying, when does someone run fast? You might say, well, a 5-minute mile is fast. Well, does that mean a 5:01 mile is not fast? Yeah, 5:01 is still pretty fast. But it's not like the fast we're looking for. So when something has a z-score of 2.9, you'd say that's almost an outlier. You'd be like, well, that's pretty much an outlier. Pretty much, but not quite. If you're being exact with your wording. You'd say, like, well, that's very unusually high, but not quite the outlier we're looking for with a z-score of 3. I just don't want anyone to think magic happens when 3, and it's like, aha, it's magically an outlier now. It's just that, that's why you'd probably just say the z-score. You'd be like, it's a z-score of 2.9. Anyone who knows what the z-score is would be like, that's pretty unusually high. And so, but it's not quite an outlier. Nearly normal condition, it just means that the data is normal. You'd not be allowed on this running team. So nearly normal condition is that our data follows the normal curve. Our data follows the normal curve. And so everything we're doing right here, here's the biggest note on this slide. You ready for the big note? The big note on this slide is the curve. Yes, the curve we want us to know over is the note check. You got it, Sarah. The big note on this slide is, for the normal curve to be applicable, we must have normal data. I know that sounds crazy, but for the normal curve to be applicable, we must have normal data. That gets into process control, Isaac. That would be very unusual, and I'll show you that afterwards probably. That's statistical process control, because now you're looking at multiple observations that are 3 sigma above the mean, and that would be unusual because it's highly unlikely. And if you're doing the mathematics on that, the mathematics would be how likely would it be to observe 3 observations, especially if it's a time series pattern. That would be very unusual. So 3 observations, especially in a row, above the mean of 3 standard deviations, that would be very unusual. You would expect 3 observations to be somewhere here, and that's statistical process control, which obviously the topics we're talking about have usage throughout many statistical disciplines. So if you have a process where you observed 3 standard deviations that far above the mean, that would be very unusual. Like, and just even 1 that far above would be unusual. So you'd be like, something weird is going on right here. Think about that. You would think that your machine would be running too high or way above the mean. Yep. Kyle, great question right here. What you're doing is you're saying, when can we use this notation? Kyle gets it right there. Nice job, Kyle. When can you do this? I know this sounds redundant, but when the data is normal. When can you do this? When the data is normal, when the data looks like the normal curve. So we've got two last big topics before we get to the assignments for today. We've got working with the percentiles under the normal curve, which is kind of what we were doing. Now, the median is the 50th percentile. Where's the median going to be on the curve? The median will have a z-score of what? First person gets the mega extra credit. Make sure you're tuning in right here. The median will have a z-score of what? The median, you got it right there. Josh, amazing job. It'll have a z-score of 0 because that is the 50th percentile, as best I can draw on the curve. The median, wow, nice job on those Streamlab points. Amazing job. Q1, I believe, has negative 0.674. You don't need to memorize that. But who can tell me where Q3 will be at? Q3 will be where? So if I were to, this is a really great test question. Q1 is this. You guys got it. You know it because it's symmetric. So that one, I'll do it the right way. I'm going to cheat. I'm going to do it inside of R real quick. It's going to look weird here for a second, but let me go to R and find out the exact answer. I'll bring in the screen over so you can see it right here. Okay. I was doing those videos. New R script. Let me bring it over here. This is why I like programming, because I can easily find out. So it's P-norm. Is that it? We can't see it. Where are you at? Oh, no. The green screen down. Well, that's... No. It's Q-norm. Quantiles, Q-norm. What am I doing? No one saw that. It's not P-norm, it's Q-norm. There it is right there. There is the z-score for the 75th. And if you notice, there's the positive right there. Brian is now finding the z-score for the what? Because I'm asking quantile, the 50th quantile, what is the z-score? What will this return when I run this now? What will this return when Brian runs this code? 0, you're right. Because that's the z-score for the 50th percentile. Now, I want you guys to think over this one. This is going to return a number very close to what? This is going to return a number very close to what? Because this is the z-score for the 84th percentile. This is the z-score for the 84th percentile. Mega extra credit first person. This is the z-score. What will this return something very close to? This is the z-score for the 84th percentile. People are getting close. No one's got it yet. The 84th. Morgan, amazing job, Morgan. You're right. Return something very close to 1. How about this 97.5 right here? This will return something very close to 2. How about this 99.85 would return something very close to 3? Very close to. Random people. And so if you notice, I'm using the empirical rule numbers right here. And so why would Q3 be this? So the reason Q3 is that is just to review. I know I went a little, if you're watching this again, maybe it'll make sense. And I'll show you some easier ways of doing this in a second. Because this right here is the 25th percentile. Does everyone see why this is Q1? Because that's 25%. And then this is Q3. And that's just the other side of it. So it would just be, as let's go back to our graphic right here. Q1 is down here, which is the lower 25%. Q3 is where the 75th percentile is. What do we mean by Q3? Q3, which is this, means 75% of the data is below that point. Q1, which is this right here, means 25% of the data is below that point. And the median, which is right here, is 50% is below this point. So don't worry about the coding part of it, but I am able to find these answers really quickly by asking the code, where is this quantile? That's what my code was saying. Just to see it again really briefly right here, all my code says is where is this quantile on the normal curve? Will this z-score right here be positive or negative? Will this z-score right here be positive or negative? You don't need to memorize that one. No need to memorize these numbers right here. But this is the big thing to know. Will this z-score be positive or negative? Negative, you are right. Because think, I'm asking for something that is slightly below. This is where is the 48th percentile. So if you're wondering how people knew that, the 48th percentile would be right about here. It's going to be a little bit below. Does everyone see that? Let's go back and look at our curve again and think about this. where I want someone to tell me, give me a guess of where the 60th percentile is. Someone give me a guess of where the 60th percentile would be. Where would the 60th percentile be? And I'll show you. I should do it the way you're going to do it. 2 seconds. While you guys guess where the 60th percentile is, I'm going to show you the way you'll see it. And let me put this site in the chat because this is going to be very important for our assignments. Okay. So here is the site. Got to make it the size. That's how to do it. Put it there. And then we put this in the chat. Got to go back to the chat. Between 0 and 1, you're right. So there's the site. And you'll notice right here that what I have is the same curve that was drawn out for you. And here it is right here. Let's bring it back up here on the screen. Here's the curve right now. Bring this down a little bit. And now what we do is this is a visualization of what I was doing a moment ago. Do you remember how I was entering in Q? I'm going to go below. All those numbers that Brian was entering in, like when I entered in 25%, see how this is right here? Everything I was doing with code, which you saw right here, this right here, let's show it. You don't have to know how to code because look at what's on the screen right now. Do you see what's on the screen? It's doing the same thing as my code. Do you see that negative 0.674? There it is on the screen. But the visualization actually shows you what's going on, that this is the bottom 25%. This is the site you will use. It is in the notes too, but I dropped it in the chat. So if you scroll up just a little bit, if you're watching the video, the site is currently in the chat from Stat to 1. You do not need to code in this class. I just like showing it a little bit just to show we can get answers really quick if we use code. And I love coding. So you don't need to code. You could find the 75th percentile, which is going to be this right here. Boom, we got it. Now I want people to tell me what are the two numbers that are going to appear on the bottom of the screen for mega extra credit? Why would the Q3 be, it's, and then not 0.674. You won't be able to use code on the exam, but it will help. Learning how to code is always a good skill for life, but you won't be able to code on the exam. What are the two numbers going to be right here? I want you to think about this. This amount of area down here, and this amount of area here, and this is the middle 50%. Brian has on the screen now the middle 50%, which means below here is what? And above here is what? This is the middle 50%. Does everyone see how this is 50? This is the IQR, you are right. But that doesn't look to be about negative 0.5. Jack, you're very close. You might need to scroll up in the chat. Where is that one? And where is this one? And how is it similar to those graphics we just saw? Sarah's on the right track. Yes, Morgan, you are right. Those are the numbers we just saw, and it's the same numbers because this is the lower 25%, this is the upper 25%, and this is the middle 50 right now. Does that make sense what's going on right here? That this is the same sort of thing as me doing this. Keep an eye right here. I want you to focus your eyes right there on that, and then I'm going to go to below, and look, it's in the same spot. If I go to above, that's the same spot right there. Watch as I do this really quick. It's almost like you can see the middle 50 between it. So if you notice right there, how do we calculate the percentile in the equation? You need calculus. And we won't do calculus in this class. We're actually removing the calculus requirement, I think. Well, I don't know. That's background stuff. I know, I'm sorry, Isaac. You can do the calculus if you want. You can integrate the normal curve. I'm not a fan of it. So all the good stuff right there. Does that make sense what we're viewing visually right here? So if a question, which we'll be doing later, asks us, like let's say a question, which we do, but when you enter 50 gives you the range. Well, you can do the top. Okay, now I'm going to ask for the top 50%. Where is the top 50% on the normal curve? The top 50% starts at a z-score of what? It's solving it for us. I hate buttons keep asking. It's solving it for us. It's telling us where these percentiles would be at. Skylar, you are right. It'd be at 0. The top 50% starts at 0. Where is this going to be? This is going to be between a z-score of what and what? This is the top 50%. This is the top something percent. This is the top something. This has to be between a z-score of what and what? And buttons keep asking. Hopefully I can explain in depth. It's solving it for us. You will not have to figure out 0.674 on your own. That's not a number you need to memorize. People might be stumped on this one. It will be between 0 and 3. Thomas, you're all right. It will be between 0 and 3. It'll also be between... Can anyone get more exact than that? Not 0 and 1. Very close, Jared. Very close. Who's got it? First person gets mega. Who gets it? Who's got it? No, don't worry, Isaac. This is a tougher concept, and this is what a lot of the homework's going to focus on. I slow it down. Devin. Well, think about this. You ready? I'm going to give you some hints here. Let me open up a new sheet. Oh, no, we should use that one. This right here. I can't see it. I can zoom out. Really? Okay, we got a new sheet. Okay. Okay. Here's how I know where it'll be. No one said in the chat yet. Don't worry, that means I need to slow down. If no one gets the answer, Brian has to slow down a good bit. It's a good thing. Yeah, my normal curves today. It's because the microphone. I'm just going to keep blaming the mic. Because if I go a little bit further over, it's going to hit it. Okay. Now, these are the numbers that we should have written down or memorized. But I want someone to tell me, after we get these numbers, these are the numbers we just did earlier. From here over is the top what percent? From that arrow shows us the top blank percent of the data. That arrow shows us the top blank, 50%. You got it. This arrow right here, and I'll even do a little bit helper right here. The new arrow Brian has drawn is the top what percent of data on the curve. That arrow right there is the top what percent of data on the curve. 16, you are right. You have to add up all of these numbers on the bottom right here to get 16%. Now, you can do the inside-outside trick like I just did to give a little help right there. And so now the next one from... Oh, I went too long. I was like, that didn't look right. From here over is the top what percent of area on the curve. Needy, you got it. Needy, great job. That is correct. So the top 10% would be where? Between what and what? The top 10% would be between where and where? The top 10% would be between where and where? Where would the top 10% be? In between the 2.5 and 16%, you are right. In between 1 and 2 standard deviations, you are correct. In between 1 and 2 standard deviations. It is between these right here, and that's between this right here. If you notice, just to make it very, very clear, it's between this right here. The top 10% has to be somewhere in there. Does that make sense? It's between the first and second standard deviations, the top 10%. To just see this visually, and we can get the answer instantaneously here. Oh, had I already clicked it? I guess it did. But that's the top 10% is somewhere in here. Now, where would the top 2% be? Now, I want you to think about this. Let's go back to our graphic that we just drew. If this is the top 2.5%, then the top 2% would be, you guys got it, you're seeing it. It would be between 2 and 3. Yep, and we're finding where the z-scores would be at, and we're inputting the areas. Is it making a little more sense, Isaac? We just keep doing examples, doing problems. As I said, today is a little bit more difficult of a lecture. Z-scores are a little bit easier. Understanding how to work this applet and everything's a little bit tougher. The top 2%, if you notice, this will be a little bit above 2, and this corresponds with what we drew over here, because we know that this right here is the top 2.5, and then the top 2% would be somewhere over here. Now, we don't have to know exactly. I like that's becoming a little more clear. That's what we want. How about the top, top 0.1%? How about the top 0.1%? Like, let's say we say where the 99.9th percentile is. So now if you look at this over here, this represents the 0.15 percentile. So it's above 3 sigma. You're right. It's above 3 sigma. So you can do this a separate way on the curve. You can go here to this curve, and you could go below, and you could say, where is the 99.9th percentile? So now I'm asking, shade 90. Don't worry, this is not, let me show it. Less people think that's the graphic. It's very hard to see, but there's a line at 3.09. I can zoom in on this, and you can barely see it. You have to look very closely with your eyes. Am I doing above? I'm doing below. Good. I'll zoom in even better so you can see it. That's so hard to see right there. Oh, you can't even see it. There it is right there. That's 3.09. I know it's so small. That's why we usually don't talk about areas beyond it, because you could, let me put this back into where we can see in the field of view. You could ask like the 99.9th percentile. Oh, there we go, did it. And that would be at a z-score of 3.719. Now, this curve isn't really configured to do things like this, but this is why I like using R, because now I could go here and I could ask for the 99.99th percentile, and I run this, and we get the same number. There's the 3.719, and there it is right there. But once again, that curve won't let me add in more numbers. I could go here and do this. You notice there's that, and here's this. And you could just have fun where you take the 9s and do something like this. And you, oh, infinity. Haha, that's fun. There we go. But so eventually it's just going to start giving me, I don't like that it said infinity, but it didn't reach infinity yet. It just, I think it oh, you know what it did? It rounded it to 1 eventually. R got mad at me and it was like, oh, are you entering in 1? Well, that would be, you'd have to go to a z-score of infinity. You won't need jump for the exams, but you will not calculate these by hand. What you will need to know how to do is you will need to know how to use the applet right here, and you will need to know how to look at these pictures. I want someone to write in words right now what this picture is showing us. Now, there's a few ways. I'll take some phrasing. What is this picture showing us right now? It's showing us an area that's shaded in, but someone tell me, explain, what is this picture showing me? And it's giving me these are, what are these things? It's a 0-1 curve. People are getting it in the chat right now. You won't need this app for the exam. Big on the homework, and you will need to know how to look at pictures of this for the exam. People are getting it. This is the z-scores for the IQR, and the area between Q1 and Q3. You are right. So this is the middle 50% of the curve, and the app is returning the z-scores. But wait a minute, we can do more with this app. Watch this. But wait, there's more. We've got here, if we put in a mean of 80 and a standard deviation of 10, these are no longer z-scores. These are no longer z-scores right here. And this means we can see the middle 50% of scores on a Stat 1 exam that has a mean of 80 and a standard deviation of 10. The middle 50% of scores would be between 73.255 and 86.74. But what if we wanted to ask, what were the middle 80% of scores? The middle 80% of scores are right here. If you notice, the curve up above shows you now the middle 80% being graphed and gives you these right here. You can convert them back into z-scores by going to the standard normal curve and just entering in this, and look, now the bottom of the curve changes from the values of in context of the problem to now the z-scores. So this lets us really quickly and visually represent what's going on. Is it making a little more sense to people why we have this applet and how we use it? I'm going to show another thing about this applet right here. How are we supposed to do this without a calculator? We'll show you pictures on the exam, and there is a way, and I will send out the videos. I do have calculator ways of doing this. Let me drop those in the chat real quick. Check out these videos if you want. You can use your calculator if you want, your TI calculator. This is probably the hardest part of this lecture, this concept right here, using the normal curve. And 2 seconds, I'll send you guys the link. Oh, wait, can I do it? Wait. Wait, is it the right screen? Can I do it? Are you guys hearing some music? I don't know. You guys have to tell me if you heard some music. Maybe. I'm jamming out to the music. I'm on the wrong screen for it. Might even hear, like, the computer. Did you guys hear the computer, or did you guys hear the music? What does it say? You guys heard the music? Yes! Working away this weekend, getting stuff done. Goomba, goomba, goomba. Yeah. I want to start doing that when we, I got a lot of fun things I did this weekend. I have to remember them. I have to put them into my repertoire. Can we take a short breather after this? I need a second to process. You got it, Jared. We're so close to being done. We're going to take a short breather at 11. Don't leave at 11, but we'll take a short breather at 11. We'll take a short breather. There's a lot of multiple choice, a lot of true falses on the exam. And so if you notice in the chat right now, I put a video link. And so the video link should send you to the Stat 1 site and show you how to do it on the TI calculator. And I show some graphics with it. You can do it on the TI calculator. You can do it with the applets. We're going to take a short breather at 11. We should be done with the main concepts of this lecture, and we'll start doing all the assignments. Do not leave. These assignments are not easy. Yeah, I think Nathan will probably need you. Good to see you here, Nathan. Please stay in contact, Nathan. Are we allowed to use jump on the exams? No jump on the exam. No jump. A lot of pictures, a lot of concepts. Okay. So I want to point out one last thing right here. Let's look at this applet right here. You ready? All I did was change it to area from a value. In the previous one, it was value from an area. So with value from an area, we're going to input the area, and it'll give us the value from that area. With value area from a value, we'll input the value, and we will get the area. So now you notice these down below here are z-scores. Well, let's change it so they're no longer. We have here the mean of 80 and a standard deviation of 10. And then we could ask right here, what percent of students will score above a 90? I want everyone to look at this curve right here and tell me what will be the answer and give a close guess to it. What percent of students will score above a 90? 16. Jack, you are completely on track. Jack, you definitely got that mega extra credit. The answer is 16%. Now, this gives a more exact answer. Does everyone see how Jack got 16%? Because he's using what we did earlier. It's the same type of questions I'm asking where Jack went one standard deviation above the mean, because on this curve, we have here, let's do black pen right here. We have here 70, or no, is it, I said above a 90, 80, 90, 100, 110. I think that's what our curve looks like. Let's double check the math on it. Yep. So I want you to notice that I'm able to draw this out on the following. I'm able to draw this out like this right here. And this is how we get it right here. So below, Gracie, amazing answer, Gracie. Gracie, you've definitely earned the mega. That is an amazing answer right there. By saying that, you understand what's going on. If I go to below, due to the rule of symmetry of the curve, then below this is also basically 16%. So this is solving the curve for us and integrating it. That's why, Isaac, we don't need to actually do the calculus. There are things like z-tables. I hate z-tables because we can now use technology and things like this to understand the areas above and below the curve. What percent of the curve is below 80? Who knows what percent of the curve is below 80? This is going to now tell me the area from a value. I'm asking, what is the percent of area below 80? Because I'm putting in a value. Oh, there's the answer. And so it's 50. You guys are right. I didn't want to show it yet, but there it is. What percent of the area is below, let's say, 75? Now, here's where people make a mistake. This is a big note. Don't leave yet. We're going to take a short break at 11. But this is the percent of area below 75. Now, what some people do, don't do this, is they cut this 34 in half. You cannot cut the 34 in half because it's not symmetric. This is not a symmetric portion to this one over here. What do I mean by that? I mean, when you have that you're interested in this area right here, that these areas like X and Y are not symmetric, and it's a little sharper than that. I know, Ethan, I hate z-tables. This is so much easier. You just put in the number and it tells you it. You're like, as long as you know how to put in the numbers, which it does take a little while to learn, I will admit. But you just say like, okay, what is the area here? And it's like, yep, that's the area right there. Boom. We got it. So now, good stuff right there. And we know the area. Nice job, Shady, right there. And now if you want to change this, you could just say, what's the area below that? And if you notice, the area is getting what as I do this? What is the area doing as I do this? Look at the area and tell me that the area is getting water. And you can watch it. The area keeps getting what as Brian does this. Do you see how it's just calculating? This right here is the area underneath the curve. You got it. So it's really quick, really easy to use. You can go between two numbers. You could say like, what percent of students make between a 70 and an 80? When I hit enter here, it was negative, so it got mad at me. When I hit enter, what is it going to tell me for the answer? A number very close to what? Between 70 and 80, it's going to tell me what? You bet it's live. It's mini term. 34, you got it. There we go right there. Very close. It is possible via calculus, which if you want to use calculus, that's cool, but it would take a lot more time. So it is possible to figure this. We're just integrating the curve because integration gets you the area underneath something. So we're integrating the curve, but I wouldn't do it. No fun. No time for that. Yeah. So this is much easier to do, and it'll tell you the area underneath the curve. You can also see that the area between like 70 and 75 is going to be smaller than the area between 75 to 80. So you notice that's a bigger area right here. So you can literally calculate all of these just super quick. Just calculate those areas with all that good stuff right here. And so good to see you, Shady, in the chat. We've got one last few things. Let's hop back to the notes. We're going to finish up this section before 11. Then we're going to come back, do one last quick section, and start working on the homeworks and the quizzes. So don't leave. These homeworks and quizzes are not easy to do. Like, please, whatever you do, don't be like, I'll just do these later tonight. Who's going to stay and work the homeworks and quizzes? Because Brian's going to work through them pretty much during class time. Definitely not easy. People have looked at them, it looks like. They're like, not easy. These are not the easiest homeworks and quizzes. Exactly. Stay and do the homeworks and quizzes, because if you're like, I'll just do them at 11 o'clock tonight. No! one project at the end of the semester, last weekend. Do not leave. Do not leave. Okay. So everything we've just been talking about here is listed throughout in the notes. As this is saying, you don't just divide the areas in half. You can't do things that are not with the law of symmetry. Oh, thank you so much, Shady. Good seeing you too. So here's the rules. Here's how to use the applet. It's just showing you stuff. Everything I've been covering is here in the notes. This is 68, 95, 99.7. It might be hard to see, but this is between -1 and +1, -2, +2, -3, +3. That's using your 68, 95, 99.7. I usually have you yelled out in chat, but in class, when we're in class. Sure, an example problem. I've been doing a lot of these. I like to do my own. You can read them in the notes, and it basically gives the answers. All you'd have to do is input these values. This is the percent of people who would have temperatures between 98 to 99.5 with a mean of 98.2 and a standard deviation of 0.7. If you notice down here, the 0.7, for some reason, this doesn't always give the last number. That's just a mistake in David M. Lane's applet. But it's giving us the percent of individuals because it's giving us the area between the values. So this right here, I don't know. Let's see here. Something like 52%. Sure, let's find out. 98 and 99.5. Gotta make sure I put in the right numbers. So let's actually get the right answer here. Take a short break. So the mean is 98.2. The standard deviation is 0.7. And that was 98 to 99.5. Between 98 to 99.5. What I say, like, is already showing? I haven't seen it yet. I said something like 52%? 58%. Oh, thank you so much. So good to wait. Oh no, don't worry. I think it got mad at the. Don't worry, we have Streamlabs on, and Streamlabs can get really. Don't worry, Josh, you're fine. Tell Heather I say hey. That's so awesome. I hope she's doing well and everything. I miss so many students. Like I can't tell you. I can tell you. I can literally see where some students sat in class. That's so awesome. Thank you. There was no. Hey, wait, Josh. We're making Josh a mod. Josh, you're now a mod. So good to see you too, Josh. You 207, right? You were 207, right, Josh? Is that correct? And 320 and 474, right? And then Heather was 320 and 474. So awesome. Yep, all those. You got it. That's so cool. No, I love seeing you guys swing by. Always swing by and say hey. So glad to see you guys. So, and we got points and everything in the chat. So there's the 25th percentile. And now we get to our short break. This is our last thing. And so we're going to take a 5-minute break right now. So if you want, go get some coffee. I might get some. I've started drinking coffee again because I think I can. Because I read my instructions. And my instructions were like, don't drink soda. I haven't drank soda. And so soda. But take a 5-minute break. Here, wait. Set a timer for 5 minutes. Thank you, Siri. So start saying like you're welcome, Rob. Like, oh god, what's going on? But this is our 5-minute break, and then we're gonna start working on homeworks and stuff. I think I might grab a coffee too. I'll drink afterwards. What questions are there right now? We still got time during our break right now. We're just relaxing for a moment. Just like relax and break. We got one more concept. I think it's so. And I will say this. Let me tell you guys this. One thing we're thinking about doing is we're looking at updating the department. Oh, and then buttons. I'll answer. You got it, buttons. One thing we want to do. So you guys know the plan is. Luckily, yesterday was a really good day for the thing that's going on world event wise, and it does show that our trend, because I'm watching the trend of it, and there is a 7-day autocorrelation pattern. Interesting his voice. Andrew, amazing job. There's a 7-day autocorrelation pattern, and yesterday was, it's not like that. There's a 7-day autocorrelation, and like 7-day autocorrelation is in here. Like weekends are good. I don't know, it's just that thing. But the 7-day autocorrelation, and autocorrelation means that when you think about correlation, correlation is when a quantitative value is explained by another quantitative value. We're literally talking about like the next chapter, correlation. It's the relationship between two quantitative values. So when something has autocorrelation, auto means on itself. So something is correlated with itself. So there's a 7-day lag autocorrelation in the residual, which just means how much we miss by. So when you look at the pattern, you'll notice that if we were to put a model through this, like some sort of a curve that goes like this, where these dips are on a 7-day autocorrelation, like the residual, which is how much the model misses by. The model has this miss, which is an autocorrelation, and this will not be on the first test. Autocorrelation is time series. But that's why, we use things like advanced topics that are based on kind of simpler topics, like correlation leads to autocorrelation, which autocorrelation is, Markov, man, nice stuff right there. You got it. So, and Bayesian statistics. Yeah, Bayesian is prior and posterior distributions. There's so much stuff going on with this. Very good stuff right there, Isaac. And then here, let me go back and answer. It's so annoying. It's all models are wrong, but some are useful. And so, I always expect the weekends to be low, but this weekend was really good. I literally update the numbers every day. I've been doing it for like 2 months. Haha. But yeah, and I don't want to talk about too much less. They'd be like, what are you talking about on your channel? I think I have difficulties with the qualitative understandings of these topics. Is a way to suggest become familiar. Your research is on autocorrelation. Whoa, I missed that. I don't know how I missed that. So on RQ norm is the first. Yes, Ben, you got it, Ben. Yeah, and Ben, send me any questions you have, Ben, on all this stuff. Can you please explain how we got 0.675 and as the z-score on the curve? Yeah, so buttons, this goes out to buttons right here. It's like this request goes out to buttons right here. So you do not need to memorize what those z-scores are. To get where the Q1 and Q3 are, you have to get the value from an area. Do you see how we're asking the question, where is Q1? So we know Q1 is 25%. That's what Q1 means, like 1/4, 25%. So now we need to go here to 25%. But this is not showing the lower 25%. This is showing the middle 25%. So this is actually the 37.5th percentile. Why? Because if 25% is inside of here, 75% would be outside of here total. So that makes this 37.5%. We don't want to view this. We want to view the lower 25%. So if you notice here, this is the lower 25%, meaning this is Q1, and then it just kind of tells us. Now, this is not a z-score. This is the context, because I'm not doing z-scores. To do z-scores are on a normal curve with a mean of 0 and a standard deviation of 1. And now we obtain the value. Does that make a little more sense there, buttons? Because it kind of just gives it to us. I have no idea what that means, Coleman. Oh, just... So if your mean is not 0, it's a normal... Good question right there, Camden. How would we do this without the app on the test? We might show you pictures on the test. We'll probably show you pictures on the test. Now, should we go soon? We'll probably show you pictures on the test. So you'll get pictures, and we'll do conceptual stuff. So a lot of the questions I'm asking, like, where would this percentile be? All these things like that. You might have to draw it out. This is all the noises. So I think I just repeated it by accident. We might hear that noise in another 5 minutes. So you have to understand the pictures and stuff like that. And then Camden asked, so if your mean is not 0, if the mean is not 0, these are not, if the mean and standard deviation are not this, these are not what's. If they are something else, these would not be what's. Who knows in the chat? Meg extra credit time. We're back teaching again. If we change these will no longer be what's on it. It'll still be the normal curve, because the normal curve means this shape right here. That's what the normal curve means. Normal curve means this shape. If we change these, not z-scores, you got buttons. That's the answer we're looking for. Buttons got some mega extra credit right there. If we change it from a mean of 0 and a standard deviation of 1, these are no longer z-scores. It's still the normal curve because the shape of it is normal. but they'd no longer be z-scores. Great job, everyone back here. We're getting everyone back watching the stream again, hopefully. 5 minutes went by. And we might try to do more 5-minute breaks. I know you guys been working so hard. This is a tough chapter, and we only have one more section of it. But do you need to standardize to find z-scores? Yes. And for some of the problems, you don't need to find the z-scores to know the answer. But a z-score is a standardized value. So you do need to standardize to get the z-score. But this curve lets you work with either the standardized values, z-scores, or the non-standardized values. So now I'm asking, what is the bottom 25% of test scores? You like those? We'll try to do them more often, Alyssa. I think it's a good idea because I know we did a lot of topics today. Like we did very in-depth stuff on this. So if people like them, we'll keep doing them because like grab some food, grab some coffee, just relax for a moment. Just be like, 5-minute break. So these are no longer z-scores here. My brain hurts. We should do a vote in the chat. You ready? We're going to do a quick vote. We're coming back here and doing a vote. Even Shady gets a vote on this. They can help us out. So let's do a poll. So the poll's going to be 5-minute breaks. Yes or no. Remember how we do polls in the chat. So you guys get to vote. Some people are saying yes. Some people are saying no. One said no as far as I know. So here we go. Let's start this poll right here. Remember how polls work. People might be voting right now. People are probably saying yes. Poll is started, but remember how to vote. Wow, can you already vote before I do the poll? So to make sure to vote right here. I don't know. It's kind of... this is a tough one. Let's see. Can I vote in this? Oh, yeah, I know. I agree. It looks like I might not get a vote. Oh, wait, my vote went in. My vote did go in. Okay, let's close the poll. How much does my vote wait till your guys' vote, though? So what did we get? Betrayal. Complete the poll. Well, the sad news is it looks like I was outvoted. I lost the vote. So I was outvoted right there. So I tried, but you guys outvoted me. I only get one vote. My vote's as much as your guys. So, kind of, Camden, you're kind of right. I was unusual, but since it's not quantitative data, I'm not an outlier. Top 10 anime betrayals. My vote counts 50-1. If everyone had come back, we would have. Everyone's probably back. Everyone not voted. Oof. So here we go. I need that sound effect. We got other sound effects. This is the sound effect screen, right? Okay, wait, we gotta reveal it this way. It's guess what the winner is. I should do that when the winner of the poll is. The winner of the poll was... Yes, we will take 5-minute breaks. Okay. Gotta figure out ways to work those things in. Okay. Okay, it's time to get serious. Let's take the deep breath right here. So here we are with our time to get serious. We got one more concept, then it's time for class. Snap the whale roads. That'll be coming up later. So, what is this all about right here? We don't have too much to learn right here. We only have 3 notes to take. So make sure you're taking your notes right now and you know these 3 things. We talked earlier that the normal curve is unimodal and symmetric. You should already have that in your notes. What do we mean by unimodal and symmetric? Unimodal and symmetric means it's got one mode and then it's symmetric around it. Horrible drawings today, but I think people know the point. And so we've got here a unimodal symmetric curve. There we go. Much more unimodal and much more symmetric. Probably better on the symmetry part of it. That is the normal model right there. Now, the question becomes, how do we know it's normal? And I did hit the normal. There we go. Stop. Did hit my timer twice. How do we know it's normal? Well, there's one way here with a normal probability plot. A normal probability plot, here's the best thing you can take. Read it backwards, right? This is the best note you can take on what this is. I want someone to decode this. It's a something that tells us the something of it being something. Who can decode for mega extra credit what a normal probability plot is by reading it backwards? It's a something that tells us the something of it being something. A plot, basically, Devin, you got it right there. Devin, you got the mega. I think you've already got it. I'm going to give one more person. Claire, the plot that tells us the probability of normal, you got it. Read it backwards and you'll see what it is. It's a plot that tells us the probability of it being normal. So maybe you've heard of things like the fat pencil test. A very important note right here is the fat pencil test is only something we use for the normal probability plot. So when we think about if you've ever heard the fat pencil test, it's only for the normal probability plot. So when you look at this right here, we always say like if you could put a fat pencil across it mostly, then it is normal. It's probably too big of one. Uh-oh, wait a minute. Oh no. Oh no. This one looks skewed, where this one looks mostly normal. It's got a little bit of outliers down here. Little bit of outliers. And that's a good question. Now we'll do a more exact way in a second right here, Isaac, of doing this. But really the big note to understand right here is that if this plot is straight, it's more normal. And when it's not straight, it's less normal. Or, I guess, we'll have an exact way of doing this. The pencil's obese. Hello, right there, Devin. It depends on how big the pencil is. So this one right here follows the normal pretty well because if you look at it, it does look normal. Exactly, Sarah. Nice work right there. Where this one right here does not follow it. So what do you want to see? Oh, we need magic pencil. You're right. Oh, no, it's not here. Space pen's not available on this screen. So what do you notice? The more straight this is, the more normal it is. So that one's not normal. And this one is normal. Wrong color scheme. This one is pretty normal because it's straight. And this one is not normal because it's not straight. Less normal. Could we use standard deviation won't tell you normality. It will just tell you how spread things are. And a great question, Devin, right here. This is not regression. It kind of looks like it because it is two quantitative things, but this is just a plot that tells us if things are normal. It does look like regression, and it almost looks like we're fitting a line, but we're not going to do a kind of regression equation for this. It's just used to see if things are normal. You will not have to calculate this by hand. So this is the big note. The more straight the normal probability plot is, the more normal it is. The more bent it is, i.e. not straight it is, the less normal it is. So that one's more bent, more not normal. This one is more normally distributed and looks like that. Uh-oh. All of a sudden, oh no, we got one more top for that. We're reviewing. Here's how you do it inside of Jump, and look at what they give you. They give you in the middle of this a straight line. They do call it a normal quantile plot. It's still a normal probability plot, just another name for it. It's also called a QQ plot or a quantiles plot because it gives you the quantiles right here. So they're calling it a normal quantiles plot. But if you notice right here, I want you to tell me, do these data points follow that line? I cannot draw a line. Do these points mostly follow that line? Mostly, yes. Does this curve look mostly unimodal and symmetric? Now, you do notice this one point here, but for the most part, yes. Does this make sense? Where this curve right here does not follow it and is more bent, and you get this line right here, let me highlight the line. That line right there is the line the points should follow. Now, that is not, it is kind of a linear model. I know there's a way to talk about it that way, but I wouldn't do that because we're not really doing regression. We're just seeing if it's normal. What is the whole point of a normal quantile plot? I just said it. The whole point of this normal quantile plot, this one would pass the fat pencil test and you're looking at most of the points. Like it do a pretty good job. This whole plot, this whole thing is trying to tell us if it's normal. Yes, it tells us that the data is pretty normal and we can use the normal model. That's it right there. That's the whole point of a normal probability plot. It's like, should we use the normal thing? Because it's like, the start of this is are they normal? So one way right here is to simply look at it. Now, I wouldn't suggest doing that, but yeah, that looks pretty normal. And what do I mean look at it? I mean, look at this right here. Yeah, that looks pretty normal. Yeah, this one does not look pretty normal. But then we can do a normal quantile plot. The 2 points I've highlighted are just kind of showing that these points right here connect. This bin on this histogram right here is this point on the box plot and is this point on the normal quantile plot. So it's that bit of information is the same thing. And that's probably our worst thing for normality. We do have a pretty... It's definitely an outlier on the box plot because if you look at the box plot thing, it's showing you that it's an outlier there. And it also goes away from the normal model. If you were to extend out your curve a little bit more, not your curve, sorry. if you were to extend out this line right here that the data should follow, you'll see that this point right here is the furthest away. Now, pretend that lower point doesn't exist. Like, that lower point right there doesn't exist. That one is the one that is kind of the most away from the normal model. We're probably not going to say that it's not normal because of that, but it's an outlier. It's something that's farther away from the model because it doesn't follow the normal model that well. So we got the one last concept here. This is it for concepts, and this is a pretty tricky one right before we get to homeworks and quizzes. So remember to stay for the homeworks and quizzes because they're tough, and you got to keep those grades high because we're averaging them with your tests. So what we have right here is, you know, when is the thing straight enough? Well, you can look at it and be like, I don't know, it's kind of, is it curved? Is it straight? What is it? What's going on with it? You don't want it to have some sort of not straight pattern, or you can't use the normal curve. So we're looking at, is it straight or is it curved? And in this previous one, looks pretty straight. In this one here, not it's more not normal, so because it's not as straight right there. So this one right here, which I think is the same data. Is it the same data? It's the same data, good. Never really noticed that till now. Because I was pointing out that one point. That one point is right back here. There's that one point. There it is right there. And what do you notice? It follows it pretty well. We did say that this point is the one that deviates the most, but we have something new. We have something new. We have this right here. And this value is a what value? This value is a what value? This value, for mega extra credit, it's a p-value. Sarah, you've already got mega, and then Justin, if you don't have it, Justin's got it too. But great job. Keep answering. Remember, you're getting those Streamlab points still. So even if you don't get the mega today, you can still get Streamlab points. And just being here for, I guess, how many? You have to do it 10 times. Being here for like 50 minutes would get you as much mega extra credit. Yeah. If you're here for 50 minutes and talking, you'll get as much as mega extra credit. P stands for probability value. That's why the P, great question right there, Camden. It is a non-significant p-value. Sarah, you're right. And so here's a saying that you need to put in the chat. First person to write it gets mega. When the p-value is low, reject the null. When the p-value is high, just let it fly. When the p-value is low, reject the null. When the p-value is high, just let it fly. Camden asked a great question I'll expand upon in a moment. When the p-value is low, reject the null. When the p-value is high, just let it fly. Ben right there gets the mega. When the p-value is low, still good. There we go. Camden's got the mega. When the p-value is low, reject the null. When the p-value is high, just let it fly. You got it right there. So Camden, nice work right there. We need to know this. This needs to be in your note. When I ask you to repeat something or write it in the chat, write it in your notes too while I'm kind of rambling right now. Write it in your notes that when the p-value is low, reject the null. Oh, you already got it? Camden, tag someone in chat. And if they have it, they can tag someone else. Be like, you got mega, and then tag someone. Thank you, Camden. We're going to do that for the last 40 minutes of chat right here. So tag someone right there. There we go. Nice job. Thank you, Camden. So when the p-value is low. Now, when is a p-value low? And what do we mean that it's significant or insignificant? So this is a review because we did this a little bit before. But a low p-value is below 0.05. And low p-values are statistically significant. The p-value, Sarah, nice work. You got it. This is a review. When the p-value is low, that means it's significant, which means it's unlikely by random chance. And so when the p-value is lower than 0.05, reject the null, below 0.05. So I want you guys to tell me if this p-value right here is low. Is that p-value right there low? Has to be below 0.05. Is that p-value there low? Nope. So when the p-value is low, reject the null. Devin, you got it. Just let that thing fly. Just let that null fly. Just let it be. Just keep believing it. What do I mean by let it fly? When you let it fly, you just still believe it. You're like, imagine if a friend said something, you're like, I'll just let that fly. Your friend's like, I can run a 5-minute mile. You're like, I'll let that fly. Or imagine your friend's like, can we go to Burger King tonight? I want Burger King. Like when I usually go through Kingsport, which I'm not going to get Burger King because I'm still on no eating out at places. But so I'm super quarantined. But like if you said let's get Burger King, like I'll let that fly. So we're gonna let the null fly. We're gonna let it be. No, I really won't. Plus, I don't know if I can eat hard food yet. So oral gum surgery, fun times. So is that like on the curve if it's below? Kind of, Jack. You might be branching, Jack, I'm going to say kind of, and I'll probably expand upon that later in class because you might be talking about a different concept. I don't want to go into that too much. It's like, yeah, if you were to plot a p-value on a curve and it had a probability, if you had an area less than that, I think that's what you might be alluding to because you might know something for later. But that would be a 10-minute talk. Okay, so here's what we're talking about most specifically right here. And Jack, if I haven't given you mega, you got it. That's a great question. Good to go. I'll wait for it. Awesome. So what I want you to see here is every time you see a p-value, what should you look at with the p-value? If it's above or below what? Every time you see a p-value, and this is setting a huge stage, you should see if it's above or below 0.05. And technically, I keep drawing it sideways. I can't draw. Not happy with that alpha. I think that's the best we're going to do. It's the best alpha we're going to get. So usually alpha is equal to 0.05 by default. I'll tell you more about alpha later. It's just what you declare as, I guess I'm explaining it now. Alpha is what you declare as statistically significant. By default, alpha is usually 0.05. People can change alpha, though. This is a big note for later on because we're only a 3-week course, so why not mention it now? People can change what it is, but if I do not tell you what alpha is, you assume 0.05. So you can declare that alpha is another value, like alpha is going to be this. Now, would this make it easier? So we'd have to define alpha as 0.10. Would this make it easier or harder to reject? Now, remember, when the p-value is low, reject the null. Would this make it easier or harder to reject? If I increase alpha, because the p-value needs to be lower than alpha, it'll be easier. This will make you reject the null more often. Does that make sense? Because think, when do you reject the null? When the p-value is lower than alpha. So if my p-value, like, tell me this. Here's a trick. You ready? Now, this is not good statistics, but would I reject the null now? Using an alpha of 0.30, can I reject the null? Using an alpha of 0.30. Remember, when the p-value is low, ask yourself this. Is that p-value lower than alpha? This is only when you redefine alpha, which you can do, but this would be very bad statistics. This alpha level is way too high, leading to too many type 1 errors. I'm not going to talk about that topic, but I'm literally covering a quarter of another lecture by doing this. But these are important things we'll need to know for later on. So what is alpha? Alpha is a number that is assumed to be what, unless you're told otherwise? Alpha is a number that is assumed to be what? What is alpha assumed to be? It's not that common to change it. Usually people just use 0.05 by default. Great question, Sarah. It's very common that people just use a 0.05 alpha. It's used throughout all science. They can change it. You can be more stringent on it. Alpha that is assumed to be 0.05. And it tells you at what point you reject the null. And you reject things that are what are to alpha. It's assumed to be 0.05, which is the commonly used idea of statistical significance throughout multiple disciplines. So people can change their alpha, and you reject when it's below. When the p-value is lower than alpha, you reject the null. So in this instance, using statistics properly right here, Morgan, amazing stuff right there. That's a perfect note, Morgan. What we would do right here is we would not reject the null. What do I mean by not reject? Be careful. There's something I hate that people say. There's a bad A word, not the 3-letter one, but the bad A word is a 5-letter one. I'm going to type in the chat, and I just never want to hear it again. Oh, it's 6 letters. Oh my gosh, I try not to even think about it. Oh no, Isaac, don't say it. No, don't accept it. Don't accept it. We never accept the null. Don't do that. We only reject the null or do not reject the null. I'll take that wording. Classically in statistics, we say I reject or fail to reject. Fail to reject means you do not. You guys are awesome. We either reject or we do not reject, which just think about this. If you do not reject this, think about what are you telling me about this data? The null says what? And I do leave these types of things on the test. The null says that the data is from the normal. Does that make sense? So when you say, yes, that's, Sarah, you got it, because we don't know that it's normal. We just don't have evidence to go against it being normal. So that Sarah's getting right there. We're not saying it is normal. We're saying we just don't have evidence it's not normal. That's weird, isn't it? Statistics is weird. But we're almost saying it's reasonable to believe this is normal. Does that make sense? We're not saying we know it's normal. We're saying it's reasonable to believe it is normal. So statistics isn't like, this is normal. It's saying, yeah, okay, reasonable to believe that is normal. Exactly, pretty much what we observed here was very likely given it's normal. That's the definition of the p-value we see. Saying that our results or results more extreme than this would occur 28% of the time given this data is normal. This is our last topic on these slides. So when we reject the null, it is not normal because the null is that it's normal. So if we reject the null, we have evidence it's not normal. So yeah, and that's right. Sarah's right, because we're not saying it is normal. We just say, I continue to believe it is normal. Like it's reasonable to believe it is normal. Like results like this would occur 28.78% of the time, given that this data comes from a normal distribution. Results like this or more extreme would occur 28.78% of the time, given this comes from a normal distribution, which is likely enough, high enough p-value for us to still believe it is normal. But if you had a distribution that looked like this right here, let me draw it on a new screen. Or why not? Here, we're going to hop over and we're going to review this topic one last time. I know a really great way to review it. Let's hop over to this screen. And this is our last topic before we get to quizzes, which I should be able to do stuff to about 1-ish. Okay, so let's think about what normal data will look like. So normal data probably is unimodal and symmetric. So we go 1, 2. Oh, that's way too big. 2, 2, 2, 3, 3, 3, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4. A lot of 4s. That's where the mode's going to be at. Okay. I think I made a unimodal symmetric curve. There's 12 values above that. That's pretty good. Okay. How good did Brian do? Is Brian's data normal? The distribution should look what? The distribution of Brian's data should look very what? The shape of the histogram should look what? If Brian achieved this, the shape of the histogram should look what? If Brian achieved his goal, the shape of the histogram should be symmetric and unimodal. You're right. So we see right here that's pretty unimodal, pretty symmetric, not perfect, but pretty good right here. It's got a little bit of right skew. Does everyone see the little right skew where the mean is above the median? You see the mean right there is above the median, so it's got a little bit of right skew. Now, the normal quantile plot, if this is normal, should look very what? If the normal quantile plot shows normal, then this should look pretty what? The normal quantile plot, which was the next thing we covered, should look very what? The normal quantile plot, normal probability plot, should look very linear. It should follow a line. And that kind of does. Now, this is because of repeat values, because it's putting all the 4s on top of each other right there. Do not worry. I know that almost goes outside, but do you see how that? You can see a little bit of where it's deviating up here at the top. But for the most part, it follows it pretty well. I guess that would need to be a little bit lower. I'd have to bring it in. And watch this. We can go right here. I can bring in that value a little bit, and I can put it more towards the center of the curve. I need to go to redo automatic recalc, which is a cool feature Jump has. Let's put this here. Let's go smaller on the window, and let's show our data right here. Why do you do that? Don't snap. Don't do it. I wonder if there's a way to make it not auto snap, because I hate that feature sometimes. Really. Yeah, that's what my computer does to me when I complain. Computer's like, oh, you hate that feature? Watch this. I'll show you another feature. There we go. Okay, so here we are right here. You're going to jump in the background again, you ready? Okay, cool. Let's get the screen the way it looked. Never complain to your computer. It has all the power. Okay, so what I'm going to do, since I've got auto recalc on, we're going to go right here and change this to 7.5. Do you see how that point's highlighted right there? And that point will come closer into the curve right there. And so it's a little bit more normal now. I know this doesn't look perfect, but still. Now, do you notice how it follows it a little bit? It's still within it. So who here thinks the p-value for this? Now we full screen again. Who thinks the p-value is going to be high or low? Remember, the null is that it's normal. Oh, yeah, Jared. Who thinks the p-value is going to be high or low? Remember, the null is that it's normal. But wait, if it's low, then we'll reject the null. Does this look normal? Should be pretty high. Justin, you're right. Justin, I like that right there. Justin, you've got some mega. If I've already given you mega, Justin, then you can tag someone else and give them, since we're in the last little bit of class right here. Let's go. Remember, they still need to be in the chat, so stay in the chat if you haven't gotten it. You go to continuous fit. Where's continuous fit? There we go. I think they moved it in this jump. It used to be higher. Here's the fit the normal curve. It fits a normal curve to it. That's way off the screen. But if you notice what it did, let me close these down. Oh, this is what people have been showing me. They're like, oh, it does a new thing. It does. Jump 15, what are you doing? I don't like it. Goodness, a fit test. Jump 15 is different. Oh, and it gives 2, and it's not normal? That's not normal. That data is not normal. Wow. That data is not normal. It's hard to tell, but that data is not normal. Let me try to make the data more normal. I can make it even less normal, but I tried. I tried my best to make normal looking data. Now, watch here as I change the values. Like if I add in extreme outliers, do you think extreme outliers will help this? Do you think that extreme outliers will make this more normal or less normal? If I make this an extreme outlier, will this make this more normal? Yeah, I would have called that. I would have bet money that that was normal. Less normal. Watch. Do you see how the p-value went way down? Do you see the p-value here is extremely low? So I probably need to change these to like... Let me try to make this look a lot more normal. Oof, didn't like that. I liked the 4 better. Let me see here. Change these maybe? Oh, that's making it more normal. When it becomes more normal, the p-value should go up. Ugh. It's so hard to tell what is normal. No one knows what normal is. Oh, we're almost there. We're almost to where it would consider it normal. Oh, went down. So that means this one needs to go down. There we go. And look, it is becoming more unimodal and symmetric. It's becoming a lot better. I really thought I did a good job on this. There we go. Oh, there we go. We're getting this curve to it right here. We're getting a normal curve. And what's happening to the p-value every time it's looking a little bit more normal? Every time it's looking a little bit more normal. Yes. Every time it's looking a little bit more normal, that's starting to look like what? It's starting to, oh, that was a bad idea. It's starting to look, so we can basically start to make it look, and look at this is following even more of the line. The p-value is getting higher. So if you notice how I'm kind of just like messing with it and trying to make it look more normal just by trying to figure out if this is helping or hurting it. I think that helped it a little bit. That didn't help it. So we need to maybe mess with this number a little bit right here. This is a bad idea probably. Yeah, that was a bad idea. I thought it was. That really helped it. Ooh, that was really good. That helped it a little bit. These 7s look weird. I think this is a problem over here. I'm just going to change these to 6.5s. Yes! That's what I thought. I thought, if you notice, what am I trying to do? I'm trying to fit it underneath this curve. Does everyone see that as this p-value gets higher, this distribution follows this line better, and it fits underneath this curve more, and the p-values here are getting higher? It has 2 tests, technically. We need to update our notes once again, do jump 15. But the p-values are getting higher. This is fitting underneath the curve more. It's looking more unimodal and symmetric. You cannot reject the null. If you notice, jump tells you when you can reject the null because the p-value gets higher, and it no longer says at the bottom of jump for jump 15 what the null hypothesis is. I really wish it said the null hypothesis is that the data is normal. That's what the null is. The null is that it's normal. We cannot reject, and this fits a lot better. This 7 is probably bad. Like one of those 7s is bad. So I'm going to change this to 6.6. That 7 was pretty decent. Let's go to 6.8. Yeah, if you look, that's really fitting under the curve a lot better right here. So we might even change. That looks pretty good. Looks pretty normal. So I was able to make this curve follow the line a lot better. You can also gauge by this and try to get the points closer there. So I could use that trick too. So, yeah. Hopefully, did this make a lot more sense how these 3 things are connected? The normal curve is unimodal and symmetric. The normal probability plot should follow the red line. And the better it follows the red line and the more normal it is, the higher the p-value. Yeah, and exactly. And this could get into a topic of power, Isaac. I don't want to talk about statistical power with observations, because then you've got the omnibus test for normality. There's a lot of tests. This is a Dr. Seaver teaches a senior level class that goes over this same topic again, but at a much higher statistical level with more tests that control for things like power, which is the ability to reject the false null, which we'll talk about later on in class. But here's your 3 keynotes. You're like, Brian, what are you saying? Okay, your 3 keynotes here are to test for normality. You can look at the histogram. Yeah, you can look at it. If it looks unimodal and symmetric, it's normal. If it looks skewed, it's usually not. And then the normal probability plot right here, if it's straight, it's more normal. The more bent it is, the more not normal it is. And then the p-values over here on the goodness of fit test, which were the third ways, way number 1, way number 2, way number 3. When the p-values are high, it's normal. And when the p-values are low, boop, 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 boop. Here we go. Low p-value again, it's less normal. And once again, I can make this look ridiculous by adding in extreme values right here. If you notice, I'm adding in a lot of skew. And please notice that my graphic up top, oh my gosh, that was ridiculous. My graphic up top looks a lot more what now? Do you see the bent nature to this now where it's not normal? And then the p-value is very low, and this does not look unimodal and symmetric anymore. Does that make sense as we look at something that is not normal, i.e. no longer unimodal and symmetric, no longer following the red line, and a low p-value, we reject that it's normal. And then when we look at something right here, we see that this, I've destroyed it. The one I had on the screen previously. Yeah. So hopefully that makes sense. That's the big concept you're thinking about. That's what you need to know for this, is that how these three graphics connect. So rewind tape a little bit and you'll see something that was extremely normal. It is time now for quizzes. Okay. Let's start working on the homework first. Let's get that homework out of the way. So let's hop in here to my Pearson. Be loading up my Pearson now. And let's get the homework done. Please, please, please realize that some of these homeworks and quizzes are pretty tricky. Always try to start them early. Email me when you're stuck on them. I might send you to a video, not just because I'm like, go look at this video. But sometimes the videos have a really good explanation that would take me more time to type out. But let's say I send you a video and you don't understand it. Email me and be like, hey, Brian, I still don't understand it. And I will do my best to walk you through it. But sometimes in a video, I know exactly where the videos are a lot of times. Like I'm not going to say, go find a video. I'm going to say like, oh, here's how to do it. And good. We do have the one due today. Yes. Okay, we got it. Okay. So we're opening up the homework. The homework only has one version of it, so we should be good. Let me go to this replace question. Okay, today's homework. Let's go to replace questions. How's chat doing? Have your homework open. Okay, you guys ready? We're going to do some really hard questions to start. Rachel's score on the Stats 1 midterm was a 78. The class average was a 74. The standard deviation is 4. What is her z-score? What is Rachel's z-score? Put it in the chat. First person chat gets it. Thomas, mega extra credit. Can anyone tell me the equation? Put the equation in the chat. And it should be 1, I believe, because she's 1 standard deviation. Who can put the equation in the chat? Who can put the equation in the chat? The answer is 1. So put the equation for those following along so you can see. You got it, Gracie, right there. Nice job. And so, yep. And Keaton, you got some mega also. So it'd be 78. You might have your question on there, Jack. Yep. So all we're doing is we're taking her observation. So this is her value of y. Make sure you know your notation. This is the value of y. This is the value of y bar. And this is the value of S. So as Gracie put, y minus y bar is the observation minus the mean over the standard deviation. And you could call this mu technically. Do we know all the students' grades? Is this a population? Is this a sample? Not too big of a deal. Next question. The mean weight of a breeding yearling cattle is 1,154 pounds. Cool info. Suppose that the weight of all such animals can be described with a normal distribution. What is this value right here? This first value right in here, which I'm hovering over, is the what for the normal model. That first value is what? The mean. This value right here is the what? Because this is normal with a mean and standard deviation. You got it. Nice job. You're following along. Excellent. You should know this notation by now. I was drawing it out a lot during lecture. That this is the mean value right here that I'm hovering over, and this is the standard deviation. So let's go to our David M. Lane applet. We can get some help right here. On the David M. Lane applet, I'm going to put these values in just so I can view the distribution. This is not required for this problem, but it's going to help me understand it. So if you notice right here, let's make it really big so we can see it. This is the distribution. Normally distributed, the big N stands for the normal curve. And then the mean is right here. That was the value it gave us in the first position. And then the standard deviation is right here. And I plug them in, and you'll do this for a lot of your problems. So it doesn't hurt to just view it visually. So we can get a guess for the first question. 1,000-pound cattle is how many standard deviations below the mean? And it is saying below. It does not want the z-score. Don't put in the z-score. 1,000-pound cattle is between how many and how many standard deviations below the mean? It didn't ask us that, but it has to be between how many standard deviations and how many standard deviations below the mean. 1,000-pound cattle is somewhere between what and what? 2 and 3. You got it. And z-score wise, -2 and -3. I think it'll give it to you saying you have the wrong answer if you put the z-score. So just so everyone knows, this is not asking z-score. I'm just going to prove it and get the problem wrong. So I'm going to subtract 1,000-pound cattle. There's the difference. There's the z-score, -2.7. But I'm going to do this wrong. I'm purposely getting this wrong. I am purposely getting this wrong. Someone's watching this without audio right now. I am purposely getting this wrong. AC, you have found the correct z-score, but remember, we're just talking about how far it is below. And I'm glad it has that error right there saying we're not looking for the z-score. It's just this. So everyone knows I purposely got that wrong. I've seen students be like, wait a minute. I'm glad. I think they changed that error message a while ago because they used to just be like, wrong. That's been a common problem people get. So we've got right here, but this is an easier problem than people realize, this next one. Which of these is more unusual? Well, look at this. We've got a steer that weighs 1,000 pounds, and we've got a steer. What's the formula? Observation minus mean over standard deviation. So just so you can see it, I'm going to write it out right here. That formula is we observe the cattle's weight of the following. I selected the black pen. Observation minus mean over standard deviation equals z-score. But it wants the... and you can, not the higher standard deviation, the bigger in absolute value z-score, Thomas. Does that make sense? The z-score that is more extreme, but check this out. This cattle is a little over 100 above the mean. This cattle is 154 below the mean. So if we get the z-score of the other one, then the z-score for the other one is going to be smaller. We go 1250 minus 1154. And thank you for asking for the formula right there. Great job, Hannah. You already got max, so you do have it. That's the z-score for the other one. And that's less unusual than is a negative z-score of 2.7. So which one is more unusual? This one right here is more. Be careful. I almost thought in my head it said less, but it's more unusual. That is the more unusual cattle right there. We got it. Okay, now we get into some empirical rule problems. This is called the empirical rule right here. And if I go too fast, please slow me down. This is the empirical rule. Now, here's a big mistake that people make when doing this problem. This problem right here, the mean would never be unusual because it has a z-score of 1. Great question, Jack. The mean is the kind of most usual value. Unless you had some really... Jack, the only time the mean would be unusual, or in situations if you had a distribution like... If you had this right here, the mean would be unusual. So the mean would just rarely to never occur in a weird bimodal distribution. Under the normal model, the mean is not unusual, but that is there's so many like, how could this possibly occur? That would not be a test question, but that's a good theoretical question. So on this curve, though, the mean is not unusual because it's the very center curve. Great questions, Jack. Yeah, you guys always make me think, like, could the mean ever be unusual? And if I'm wrong, if I say things that are not, or if you guys think of another way, tell me. So what do we have right here? We're going to use the empirical rule, the 68, 95, 99.7 rule. And you need to make sure that you're using this. If you have your drawing, if you did your drawing and have your note-taking quiz done... Oh, Gracie, just email me. I'll fix it. Change your YouTube login. Change your YouTube login. Give that a shot. That's weird. Yours. Cool. Go ahead and change your YouTube login. You guys are crazy. Okay, so what do we have right here? We have the top 16% and the lower 16%, and we have here the middle 68%. Now, do not use for these problems the David M. Lane, because the David M. Lane right here gives you exact answers. If you notice on the curve, what percent of area would we expect to be above 1? I want you to take a look at the graphic right here, and I want you to tell me what percent of the area would you expect to be above 1 standard deviation? What percent of the area would you expect to be above 1 standard deviation? My hair is just everywhere. What percent of the area would you expect to be above 1 standard deviation? You're right, William, it's 16%. And we did this drawing earlier, and we can use it for these problems. So if you drew this out, this will be a huge help for these problems. This is your next note-taking quiz due Tuesday night. But if you go to the David M. Lane and put in above 1, if you say, well, what's above 1? Do you see that's shading above 1? You'd be like, oh, it's 16%. No, it's not. It's 15.87. So 15.87. So I might, if you can change your name, I'm just going to keep deleting messages until go change your name to something. You can choose whatever name you want. There we go. So change your name and maybe email me and I can walk you through instructions if you need. But change your name and then, yeah. There we go. Give that a shot. Remember, these lectures are recorded, so you can come back and check it out later. Awesome stuff. And with that in mind right here, we see that we have the mean of 28.8 and a standard deviation of 5.2. A mean of 28.8. So the mean is right there. We're good on the mean. A standard deviation of 5.2. And if you notice, this one has too small of a standard deviation. Standard deviation behind my head is too small. That's too little. We need 5.2. So that one's wrong. That is the incorrect standard deviation on the curve. Can't use that one. This one right here has too large of a standard deviation. Why is it too large? Because these, wait a minute, that one's too large. This was 5.2. This difference, you got it right there. Yep, Devin, you're seeing it. It has the right mean, and this goes down properly, but that's not the right 5.2 distance, because that's what standard deviation tells us. You can use the David M. Lane to draw it if you want. If you put it into David M. Oh, that's awesome. The deal. I appreciate that. Cool. Thank you very much. You guys are cracking me up. Okay, so the middle 68% of autos would be between z-scores what and what? The middle 68% of autos would be between a z-score of what and what? The middle 68% of autos would be between a z-score of what and what? Yep, you got it. And so, yep, it's just because, remember, you can see it right there. You got it. So 23.6 and 34. We're just taking the numbers right here because we can see the middle 68%. Use the graphic up above to help you. I need to do my enter trick. This wants what percent of autos should get above 34? Yes, we can kind of see it. What percent? Okay, wait. Brian's going to hover around the screen real quick. What percent is between my hands right now? What percent is between my hands? Between my hands is what percent? What's in between my hands? 68. What's outside my hands? What is total outside my hands? What is total outside my hands? 32. What is this hand worth right here? What is above this hand if that was 32? 16. That's got it. So that's what we have. You can see my key light over there. So that is the 16% right here. So we were able to figure that out. And remember, you do have your drawing, if you need it, as a helper, because all we're doing is going right here. Let me draw a line on it so you can see what's going on. But we're just going above this right here. Space Pen's helping us out. We're going above this area right here. How did you find between 1 and 2 sigma? You have to subtract these areas right here. You have to subtract the 2.5 off of the 16 because you're just getting that area. You don't want the full thing. Does that make sense there, Isaac? You don't want to take the full area. You want the area above 1 minus the area above 2. So you want the area above 1 minus the area above 2. Well, because we know these areas, because we know the area above 2 is 2.5, and we know the area above 1 is 16. So we've computed these so we can subtract off of it. Now, you can't cut this in half right here. You can't go to 1 and say, let me cut this in half, because that's not symmetric right there. You can't cut that in half. But if you know, yep, okay, cool. No, great questions, Isaac. Keep asking. When something, yep, that's what I like to see. This is review right now. And keep asking anytime something is like, I don't understand how you got that, or why can't you do this? This is the area above a z-score of 1. About what percent of audios should get between 34 and 39.2? Someone convert 34 and 39.2 to z-scores. Convert 34 and 39.2 to z-scores. Who can convert 34 and 39.2 into z-scores? What do we got for those? Be careful. Be careful. Close there, Thomas. You got one of them. Close. This is a z-score of something. 1 and 2. 1 and 2. Because this is a z-score of 0, This is 1, and this is 2. Here, this will help out. Thank you for asking that. I think, Thomas, you've got it. You got the mega. Thomas, tag someone in the chat and give them mega extra credit. Tag someone in the chat and give them mega extra credit. I like that you said you're confused. It's a very good question to say when you're confused. So what it is this is a z-score of 0, this is 1, this is 2, this is 3. Whenever I do this, I always like to put the z-scores in the context below it. There you go, William, you got some mega extra credit. Because you know what? It's just extra credit right there. Great job on that extra credit. It even goes above my head. So we got the extra credit right there. So, so with this right here, what do we see? We see that we have the z-scores. And the z-scores, does this make sense? Yeah, I think you see it now, Thomas. Tell me if you don't see it. You already have mega. William, you can tag someone else. It's a game of tag right now. So it's a game of tag. If you see someone else in the chat, this is why stay till the end. If you don't have mega, you stay to the end anyways. But still got 10 more minutes. We'll get the homework done. We'll do the quiz next. So interesting stuff. Let me look at. I'm gonna double check some stuff later. Okay. Continuing on to the next question. Next question. So since this is a z-score between 1 and 2, the best way to find out the area is to go back to our graphic that we've drawn. Now, we did this earlier. So in one of the boxes, I typed in a number yesterday and it is not letting me change it now. Restart the quiz, the homework. I do not know. Submit the answer. We'll try to fix that, Tyler. Sorry about that, Tyler. The area between 1 and 2 is going to be this area right here, 13.5, found from subtracting 2.5 and 16. So the area is 13.5 because it's the area between, and we're not using these numbers right now. The area is this one right here. Why did the arrows go out of the chart for 90? For 90, because, so I might be able to answer that. Why did the areas go outside? 95 is contained between here and here, but above 2 is 2.5, and below -2 is 2.5. So that's the area completely below -2. So if you were to go all the way across here, this would be the whole curve, because this is all the area below -2. This is all the area below -1. Does that make sense there? These are complex topics. These are tougher things we're doing right now. Like I said, today's a very tough lecture. It's why we spent the whole class period on it. So does that make sense to everybody right there? This is like all the area below -3. So that's every bit of area below it. Like that would extend out completely, like all the way to -infinity. So 95 is between 2 and -2. Claire, amazing answer right there. 95 is between -2 and 2. 68 is between -1 and 1. And 99.7 is between -3 and 3. That's why we say 68, 95, 99.7. So it's the amount of area contained between so many standard deviations. People are almost to 1,000 points. Great job. I want to see people get to 3,000 though. So remember, that's where the mega crazy extra credit is. Good questions in class today. Great questions. So this is between 1 and 2 standard deviations. Make sure to stay on track with your question. Let me check one thing right here. Checking some stuff out. Checking checking some stuff out. Executive decision times. You got it. There's an executive decision right there. Executive decisions were made because I think, as far as I can tell, there we go. Cool stuff. Cool stuff right there. Please tell me if, I'll double check. I'll double check that all later. Let me take a note on that. Got it. Okay. So with that in mind right here, executive decisions were made. So with that in mind, like we all know, like did Calzone Tyrone come by? He's my favorite. So I mean, we are near the end of class. It's like people. Calzone come by. He did an office hours. That's what it was. Man, he is fan favorite. Calzone Tyrone. He is like, his name is just fun to say. He is fan favorite right there. He comes by, says hey. What's happening? Like, so good to have you. We had Shady in here earlier. So I like having the people who just come and check it out. And then if someone's pulling us off track, I'm like, don't mind you being in here, but don't pull us off track. Let's go right here. We've got the next. You guys ready? I can reverse. Like if someone makes an executive decision, I can reverse it. So let's go right here. Oh my gosh. How many questions are on this quiz? This is crazy. There's 20 different ones to do. Okay. Here we go. We got this. You ready? Are the quizzes normally harder than the homeworks? They're about the same. The harder part, this is part 1 right here. I like his name too. I really want a calzone too. I doubt calzone's really his name. No, and I was like, is like calzone like the pizza calzone? I want to try one of those P-zones from Papa John's. Is that how you say it? I am so hungry right now. And all I've got is like yogurt. I want some Burger King. So I think we did this one just a moment ago, so we don't have to do this one again. You can get lucky. Now there's only 5 on your guys' quiz, but I'm viewing the whole thing right here. I'm viewing every question. We're gonna go for like another hour. Papa Dia right there. Someone's got to tell me how that is. Great job, Alyssa, right there. You got mega. You stayed here towards the end, and thank you. You got the. I just like pressing this button now. You got the mega extra credit right there. Nice job on that. So I don't think there's a sound effect on that one. I got to put a sound effect on it. The Papa D is good, folks. Oh man, I wonder what Papa John thinks about that. So I saw him on like H3H3 podcast, and they're doing like those pizza tests. He's so exact. I mean, craziness. So, but my gosh. So, man, now I just want that because I love calzones. Oh, but no, it's not like a calzone. I think I just want pizza. Okay, you guys get ready to serious here. Let's do it. Did we finish chapter 5 homework? We did. We finished chapter 5 homework part. Wait, did we not do the last question? I think we didn't do the last question, right? Correct me. Sorry, Brian got sidetracked. That happens. So we didn't do the last question, I think, right? So with us not doing the last question, let me go back and do that. People are probably saying that in the chat. So let's go back to the homework. Back to the homework. That's not homework. It's quiz again. Homework. Preview. Last question. Sorry about that, everyone. We got this. You ready? Last question right here. Let's do the homework. Finish it up. Sorry about that, everybody. Randomness. You guys got it. Of course, it's random right here. It's random all the time. Random every bit. Whatever happens in class is completely and utterly random. So let's do this last question right here. We see that there is a mean of 10.5 and a standard deviation of 4.75. So with a mean of 10.5, there's the mean. Oh, this one's got the wrong mean. Do you see that? Wrong mean. That's not the right mean. And then we need a standard deviation of 4.7. So, we didn't do, sorry. I have to redo the question. No. Where's the right mean and standard deviation on this one? This one's right. And then I'm just doing it quickly because we've already done most of it. And then this one goes the middle 95%. It's the middle graphic. That's that. That's the middle 95. Should get more than 33. 33 is at a z-score of 1. And so a z-score of 1, above that would be 16. Does it say more? It says above. Good. And then this is between 33 and 38. That's a z-score of 1 and 2, so that's 13.5. And here's the last one. Describe the worst 2.5. The worst 2.5 is a z-score right here because this is the bottom 2.5, so I'm going to slow it down right here. The z-score of the worst 2.5 is a z-score of -2. So everyone see how this is 2.5 right here? So I need to go 2 standard deviations below the mean. And we go back, and we see that 2 standard deviations below is 17.5. Jimmy Neutron's here. Love your show. So they would get less than this right here. Good stuff. Clap, slap, slap. Clap, clap, clap. Some Bulby right there. So, Jimmy, I need to finish Jimmy Neutron. So, with someone special. And so, here we go on the last one right here. We need to get the right mean and right standard deviation. You're a Sheen fan. Sheen is awesome. I can't remember. I think it's Phil Lamar who does the voice of Sheen, and he did the voice of Bolby. He did the voice of Bolby. I know that. Which one of these is correct? Oh, Brian. Oh, look at this one. We got 68 right here, 95, 99.7. This one is incorrect right here. This one is incorrect. As in, this one is the correct one. Is that a Sheen reference? I'm going to finish that croissant. It is C because why is it C? It has the right numbers, as they both do. But then this one right here is 68% right here, where this one is 99.7. So if you notice, it's not doing the 68, 95, 99.7 rule because it makes sense that 68% would be the central 68%. It wouldn't be, you can't have 68% further out. So we have all of this right here. A forester found. We understand what this is. It's just data measuring trees. They are tricky, you bet, because the 68% should be right here, and this one doesn't. And I think you guys are getting it because if it wants the middle 68%, we just go to the numbers on the curve, and that's contained between these values right here behind my head. So we have 58 right here. 5.8. And then we have 15.2. How am I getting these values? These are the values of the middle 68% as shown on the curve between 5.8 and 15.2. You got it. Now we want what percent of trees should be below 5.8. I want someone to convert this to a z-score who doesn't have mega extra credit, who wants the mega extra credit. So who's going to get the mega extra credit right here? Convert 5.8 to a z-score. We want the trees below 5.8, but turning it to a z-score. Jose knows the answer. So great job, Cooper. And Jose, you get the mega extra credit right there. And Camden also. Camden tags one. I think you've already got it, but you can tag somebody. Elizabeth, let's also give Elizabeth mega extra credit too. The area below 5.8 is going to be 16 because it has a z-score of -1. That is correct. And if you notice right here, we're at -1, and then we're going to the area below it. I think so. Chayatune, if I am pronouncing it correctly, you tell me if I am pronouncing it incorrectly. You're still here at the end. Haven't given you mega extra credit right there. So Chayatune, you got mega extra credit. Awesome. Please tell me if I'm not pronouncing that correctly. You can email me or say it or give me the phonetic in the chat, and I will correct my pronunciation. So there we go. Great job. You guys know what's going on with these questions. By converting this to a z-score, we can see at a z-score of -1, the area below it would be 16%. That's because 16% is inside of there. It's hard to do, but 68% is inside. 32 total, 16 in either hand. It's probably better explained by what we were doing throughout the lecture today when we see that 68% is inside of here, between -1 and 1. 32% outside is total, but below here is 16 because that's half of 32. Remember, review today's lecture, and we went through this in a speed run and a slow run, so check that out. We go right here, and there it is. We check our answer. At what percent how would you calculate the percent between z-score of -1 and 0? Can someone help us out here? Thomas wants to know the area between -1 and 0. So what is the area between a z-score of -1 and 0? Let's help out Thomas right here. Mega extra credit, first person to help out Thomas. Thomas, you already got mega 2. 34, William, great job. 34 because it's half of 68. Great job. You're following along. You're doing it. So it's half of 68 between -1 and 0. So great job, Thomas, right there. That might have been a problem you're working on. So Thomas, excellent work. Yeah, no, don't worry. If you didn't ask, you wouldn't know. Thomas, that is amazing. Thank you for asking. So great job right there. Remember, if you already have someone tagged, you can tag someone else because he's giving a tag at the end of class. So that is awesome. I really am too. Please ask questions when you're stuck. That's what we're doing. We're here to help each other. This is 19.9 to 24.6. So 19.9 to 24.6 is right here. This is a area between 2 and 3. Be careful. That's the area between 2 and 3. You guys know Stats Nation. We got to start putting stuff out like that. Like, what's up, Stat Nation? That's so cool, Jose. You're awesome. I like that right there. Jose, definitely. I'm going to keep bumping the mic. Jose, great job. I really like that idea right there. Jose, you can do that. And I'll tell you guys when you can do that at the end. So Eric has got it right there. Because I'm doing between 2 and 3, I'm going to go back to my graphic to help me out. Can anyone tell me the area between 2 and 3? Great job, Camden. Can anyone tell me the area between 2 and 3? And you can always go, but if you've been doing 2.35, you got it. That's the area between 2 and 3 because I identified on the curve that I'm talking about between 2 and 3. You have to use the numbers you're given to say what are the z-scores of these. You scroll back up here, and the z-score was 2 and the z-score was 3. So this is going to be 2.35. And I used my graphic we drew earlier to do these answers. If you can't tell, that graphic was very important. What percent of trees should have diameters over 15.2? 15.2 has a z-score of 1. So we go back to our curve and we look at the z-score of 1. And a z-score of 1 is like our earlier question. With a z-score of 1, we would be right here. And it's going to be 16%. Above this is 16%. So the z-score of 1 is the area right there. And it's very easy to do with these curves and stuff to see that it's 16%. 16%. And here we go right here. Above. It says over. Watch out. It could say over. It could say under. That's an easy way to make a mistake on these. And it is a z-score of 1, right? Let me double check my work. We've been doing so well. It is a z-score of 1, and that's 16%. You can kind of see it here also because 16% would be above this. Half of 32. And we got it. We have now... Oh, one more? Oh, because I didn't do the full thing. Well, let's get the 100. Why not? What is her z-score? Her z-score here is 2. That's that one. What is... We did these earlier. I'm doing them very quickly because of that. How many standard deviations below the mean is 1,000? So we do observation minus mean divided by standard deviation, and that's 0.89. Standard deviation is below. It's not asking z-score, it's asking standard deviation, and 1250 is further away. We got it. So we're just doing part 1 today. We will do part 2 in class tomorrow. Do not wait to do these. Do not wait to do these. Do not wait till 11. These are not... As you can tell, I've done these a lot. I know how to do them, but who got 100 on the homework? The quiz is going to be very similar. We're going to do a good bit of the quiz now, but who got 100 on the homework? Did anyone? Nice job, Morgan. Yep. So I wanted you guys to get the homework done, and I suggest staying for the quiz right here. I won't be able to put the tags in the video till later tonight. Very sorry. You emailed, yeah, and then we should fix that. So as long as you have an 80, and then you can go down here. Similar question. If you need to redo a question, you can always do similar question. You bet, Keaton. I'll do that here in just a little bit. The homework, Keaton, the homework or the quiz? The homework or the quiz are you looking for, Keaton? Because quiz can change order. Yep. No taking quiz due tomorrow night. Part 2, chapter 5, part 2 is tomorrow night. I changed the date on it. I should have. I think it's changed. But I changed the date on it. I got a question on one of the quiz problems. Yeah, let's do that. Which one are you working on, Jose? Jared. Sorry, Jared right there. I saw the J. And so which one are you working on? Tell me the start of it and I'll find it. So if you're working on a quiz problem right now, you can tell me any quiz problem you're working on. And I will find it. I will find it and I will solve it. If there is a problem. I don't know what it is, but I will find it and I will solve it. Please do the one with the IQR and new median. Is that on this one? Is that on this one? Oh, I know. Yeah, okay, that one. Okay, let's do that one first. So we got shifting data by adding a constant value doesn't change it. Yeah, cool. So how it starts out. Fuel economy. These are very similar. We did that one. That one's very similar. Is this it? How's this start out? Can we do the one about the exam scores? Cool. We'll do the shifting one first. Shifting data by adding a constant to each value. Find that. Okay. Ah, here it is. Cool. Okay. Shifting data by adding a constant to each value does not change the what. Okay, let's think about this. You ready? Shifting data by adding a constant to each value. Let's do that. Let's take a data set right here. You ready? We have a data set right now that is 1, 2, 3, 4. Does that make sense? I'm going to add to this 10, 11, 12, 13, 14. Can anyone tell me something that changed for this? Here's data set 1. Here's data set 2. Something that changed for this. What changed about this? Sorry, sometimes they can be a little crazy on the point allocation. I'm sorry about that. So what? No, the z-scores would actually not change. Good question right there. Did the standard deviation, is this data spread out more than this data? And by spread, I mean kind of like, so think about this. The mean changed. The mean was 2.5. The median's also 2.5. Does everyone see that the mean has changed? The mean has changed. Here, we'll do Devin's next right here. I think you're putting, Devin, remind me, we're going to do that one next for you. So the mean has changed. The mean and median has changed. But the data has not changed the what of the data. The data has not changed the what of the data. The measures of what for this data have not changed. The center has changed, but the IQR, which is a measure of spread, and the standard deviation has not changed. So you would still have the same standard deviation, and you would still have the same IQR, the variation within the data. The center of this data has changed, but the spread of the data, we'll do as a black, meaning it has not changed. The spread of the range has not changed. The IQR has not changed. The standard deviation has not changed. We'll do Isaac's next right here. So we got Devin's, then Isaac's in the queue. So when the question asks, shifting the data does not change the what, it could be standard deviation, IQR, or range. So right here does not change the... Let me just double check. Yeah, the quartiles will change because that's the 25th percentile. Yeah, that will change. Standard deviation is the only thing that doesn't change. The IQR won't change because the IQR is a distance that the quartiles are apart, but the quartiles will change. Like the 25th and 75th percentile are different. Let me show that visually. So the 25th percentile has changed and the 75th percentile has changed. That's where the 25th percentile is and the 75th, but their distance apart has not changed. So it could have said IQR. IQR here has not changed because the distance between them has not changed, but the quartiles have changed. That's very tricky right there. If you multiply, which is a good extension of this question, which I think another one asks, let's take and multiply these values by 10. So if we multiply these values by 10, we got to erase a lot right here. So the red means it's changed. Multiply these values by 10. Then we got Devin's question next. So now what has changed here? The spread of the data has changed. The IQR of the data has changed. The median and mean of the data have changed. So I think what has not changed? Does it say was not changed? Let me look at the question. I'll find this version, then we're doing Devin's next right here, because this is kind of an extension of this question. There's one like if you multiply. Where is it? Was that Devin's? That might have been. I saw that one earlier. Standardizing values, turning them to z-scores. Shifting the data by adding a constant. Same question. Oh. Well, maybe there's not that one in there. Multiplying would change everything. We have put that on test before. It's possible. Random. So we could randomly give you the same question. Devin's question was, suppose your statistics professor tests grades or z-scores. Let's do that one. Suppose your statistics professor's test grades or z-scores. Here we go. Okay. Suppose your statistics professor's test grades. What was that website? David M. Lane's site. I'll drop it in the chat right here for you. There you go, right there. And suppose number 18 on yours was the one that does not change, by the way. Okay, good. Yeah. This is the one that uses your z-scores equation and solves for the observations. Sounds like it. Oh, so you have to use David M. Lane right here. Cool. Suppose your statistics professor reports test grades as z-scores. You got a z-score of 1.81. So what does this mean about your grade? Your grade is what? Your grade is what? Your grade was a what? Your grade was 1.81 standard deviations above the mean. Now yours might be that too, yeah. Just depending, it's like how many above or below. And so I want someone to tell me if we were to have the following. If I want the black pen. If you scored 1.81 standard deviations above the mean, What did you score on this test? Interestingly enough, you scored a 98.1 because the standard deviations here are 10. Now, this is a made-up part of this problem. But if you notice, great job, Devin, you're getting it. If you were able to do that and understand it, you're following along really well because that is 1.81 standard deviations above the mean, and a standard deviation here is 10, so I just times 10 by 1.81, added it to the mean of 80. Boom, we got it. So we kind of understand what's going on right here. This is where this person scored. And apparently your friend, it didn't give these numbers, but I think it helps to give fake numbers sometimes to solve it. Your friend scored down here. So this is friend right here. Friend's not happy. They got a -2 as their z-score. And their actual observation is equal to 60. If you notice the notation right there, we've got a z-score of -2, meaning they're 2 standard deviations below the mean. And we have that they're in the bottom 2.5% of the class. So they're at the bottom 2.5%. You're very near to the top 2.5%. They actually did more worse than you did better. Their observation is more unusual than theirs. That's a better way of putting it. Their observation is more unusual. Suppose your statistics professor reports your grade. The score was 1.8 standard deviations above. About 2.5% scored lower than your friend. How do I know that? We should get this completely correct. Good, we did. I'm always afraid of making a little mistake right here. But the reason I know that 2.5%, just going to drop the pen again. The reason I know that 2.5% scored below your friend is what percent of people scored between here and here. Now, this is not you. This is the middle. Those. Yep. There we go right there. And this is it right here. So now you know this has to be 2.5 up here. There was the microphone. And 2.5% right here. So that's how we know it's 2.5 because we used the 95. Yes, it also covered Chapter 5, Part 2 today. Yep, I covered everything you'll need for Chapter 5, Part 2. And it's a tougher one. Don't wait to do these till very late. These are tougher. Don't wait to do these till very late. Don't do that. Don't do that. Which one was Isaac's? Isaac had one of these that we're going to do. And then looks like Jose has the next one. So we got Isaac's question was a company selling clothing on the internet. 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 I'm just repeating it so I don't forget it. Here we go. You ready? And then Jose, we got Jose next. Remind me if I forget Jose. Be like, wait, you said I was next, Brian. So we go. It said 15.9. It might have accepted that, and it should accept 16. Are they seriously? Jared, please send me that right away, because if they're doing 15.9, I'm going to be really mad at my Pearson. Send me that right away. I'm going to see if it has the plus or minus. It might have 15.9 plus or minus 0.1 on it. It might tell me if it says like the plus or minus. It's okay if they did that. They should really, because we're using the empirical rule here. And if they want to go exact, they'd use David M. Lane. And you must have had a z-score below -1 or above +1. How will the exam review work when, how will exam, we'll just have a review. Or, and then you might get pictures or you might have to use the empirical rule. You're welcome, Ben. Great job, Ben. Excellent work. Yeah, send me that and I'll be very unhappy with that. The company plans, okay, wait. So the median weight is 53 ounces. Okay, the median weight is 53 ounces. And the IQR is 40 ounces. Okay, cool. So we've got here the median and the IQR. The company plans to include a sales flyer weighing 3 ounces in each of the packages. Okay. So with this one right here, it might help to do a little bit of a drawing and see what's going on with this question. So we've got here that we have a median and IQR. So we got that one next. We got Jose and Gracie next. Great questions in the chat. So I want you to pretend that all of these packages right here weigh something like 1 pound, 2 pounds, 3 pounds, and 4 pounds. I know those aren't the numbers, but they changed the numbers, so I'm changing them too. And then we're going to add a flyer to this that weighs 0.1. So let's draw down below here if we were to add the flyer. Now we're adding a flyer to each of these things right here. Why not? The flyer will weigh a pound. It's a very heavy flyer. So now we've added a flyer to every one of these packages. So here's the flyer. So the flyer has been added to each of these packages. Now, did the, let's look at what it asks, if it changed or not. The new median will be what? So what happens to the median in the example I drew right here? The median was previously right here. Now the median is right here. The median simply has the addition of the what? Do you see it? The median for the data will now have the addition of the weight of the flyer. The median was 2.5, and now the median is 3.5. So to find the new median, it's just a constant add to everything. So the median right here is going to be the weight of the flyer added on. We have a median weight of 40, and then we add a 3-ounce flyer. So the median is just going to increase by the weight of the flyer because it's just going to shift everything over to the right a little bit and change the center of the data. Now the new IQR, maybe it's new, maybe it's not. When you look at the IQR right here, the IQR is a distance. So if we add a constant weight, is the data, try to give some hints with the colors, is the data more spread out or spread out the same? Is the data more spread out or is it spread out the same if we add a flyer to each of these? Is it more spread out or spread out the same? Like, is the distance right here the same distance? Because we're saying like a constant weight. Yep. So this is the same right here. So the IQR does not change. The IQR will stay exactly the same. It's going to have the same spread of the data. Then it says, if the company recorded shipping weights of the packages with the flyers in pounds instead of ounces, what would the median and IQR be? It says with the sales flyers. Now make sure to do with the sales flyers. Now this is just a constant shift to the data. Hopefully I do this correctly right here. 56 divided by 16. There's 16 pounds and 16 ounces in a pound. I believe so, Isaac. I believe so. Google it. Please tell me if I'm wrong. I'll throw someone extra credit if I'm wrong, but I believe there's 16 ounces in a pound. And so we have right here, this would be 3.5. And then make sure you know it is including the flyer. So the IQR now, wait, I did it correctly, right? Let me double check. Cool. And then now we do the IQR is 40. And that's 2.5. And we check our answers. 100. Woo, got him. So let's go back here. It was Jose's question next. A town's January's high temperatures. Let's find it. I think it was about here. A town's January high temperatures. A town's January high temperature. Oh, it was at the start. A town's January high temperature. There we go. Cool. I've gotten this one wrong before, too. Like, I remember when I get something wrong, and they're like, oh, no, it was one I got. And then we got Gracie's next. So now we go, a town's January high temperature averaged 36 degrees Fahrenheit with a standard deviation of 10, while in July, the mean temperature was 77 with a standard deviation of 8. That would mean temperatures in July are more consistent, where temperatures in January have more variation in them, because larger standard deviation. Temperatures in January are also lower. They have a lower mean, which means a lower center to the data. Which of the following statistics change by multiplying each value by a constant? I think they're all going to change. The mean changes, the standard deviation changes, because the data is going to get more spread out. Just to show that one real quick again. Here's what the data looks like when you multiply by a constant. The mean and median change. The range changes, so there's the range changing between the values. The IQR changes, and the standard deviation would change too because the data is more spread out. Standard deviation is a measure of spread, so everything should change right here. And then we can do that one next. Great job. Stay in chat. Ask the questions. We will answer them all and explain them all in pretty good detail. So is it more unusual for a 55 temperature day? Okay. So here's what we got to do. We got to turn this 55 into a what? Who can help me out? I need help. I'm forgetting things. It's in the last chat right there. But I need to turn this 55 into a what? I have to turn that 55 into a what? Joseph, you've got some extra credit. You stayed till the end right here. Joseph's got some extra credit. I don't think I've called your name yet. I need to turn it into a z-score right there. Tomorrow night, there's the note-taking and also a quiz. So I think that's it, Jared. Great questions. So we go right here. and we go observation minus mean. I observe 36. I subtract the mean. I divide by the standard deviation relative to it. That's a z-score of negative 1.9. Now I turn the other one into a z-score. I go observation minus mean. Did I do it correctly? Let me think. Observation is 55 minus mean of 36 divided by 10. It's positive, but that makes sense because it's unusually warm. Yeah, we'll do the rivet one. So we got that. I think Gracie, then Isaac next. You're welcome, Jared. Awesome job. Stat Nation tomorrow. You got it. You start saying at the start. So if you guys come up with it, it's awesome, and I really appreciate it. Oh, this is going to be more unusual. I can already see it. There it is. Oh, but it's negative. Observation. Wait. Observation minus mean over standard deviation. I'm doing the formula y bar minus, right here, I'm doing this formula. Y is my observed value for the month. Y bar is the mean value for the month. And then S is the standard deviation. And the z-score tells us how many standard deviations something is above or below the mean. So the first one was 1.9. So it's more unusual in July. A high temperature of 55 in July is going to be a z-score. Oh, it asks standard deviations below. 2.7. It's not giving it as a z-score. Don't put it as negative because it just has this. And then January is 1.9. Now they're both, this is pretty high for January, but this is extremely low for July. Did I get it right? Yay, we got it right. How do I get worried? I'll forget a decimal or something a lot of times. Then it was, I think, Gracie. Please tell me if I forget. Wait, it was Joseph or Jared? No, it's Gracie, I think. So Gracie had the next one, I believe. Please tell me if I forget somebody. It's Gracie, then Isaac. An incoming MBA student. An incoming MBA student. We're doing the incoming MBA student. Incoming MBA student. Where are you, MBA student? An incoming MBA student took placement exams in economics and mathematics. In economics, she scored 80. In mathematics, she scored 87. Now, I want you guys to tell me, which of these scores would you be more proud of? If you got a 90 in underwater basket weaving, or if you got a 90 in honors senior level quantum physics. You get a 90 on a test. What would you like that 90 to be? And I'm going to let you get a 90 on one of your tests. Underwater basket weaving, you get a 90, which is kind of interesting. Or honors senior quantum physics, meant for PhD students. PhD honors quantum physics. So if you notice right there, the 90 is not the same thing. Imagine this. Here's another example, and I'll tell you why I'm pointing these out. I'm going to give you two more. I want someone to tell me if two more is a lot. I'm going to give you two more. Quantum. We'll have Isaac help us out with that. I wonder what you think of quantum physics. Every time someone mentions it, I don't hear people who know quantum physics talk about quantum physics. Oh, you really are? Quantum mechanics? Oh my gosh. Quantum is the very small, right? And then you got like astral and stuff is very large because things act, it's legit just probability. Oh, I should learn some quantum physics, quantum mechanics, but it's how things act at, I believe, the very, very small level. So I guess it's a lot of, is it matrix and stuff like that? Like linear algebra, matrix algebra? I know enough to know what quantum mechanics are. And I just know things act very weird. They act differently at the very small and at the very large. So we're still learning about the world. Like, Einstein's theory of general relativity is our best understanding of the observed phenomenon of gravity. And why do we call it a theory? Well, it replaced Isaac Newton's theory of gravity, which replaced, or we could say improved upon, non-classical ways. Yeah. And there's some way to understand them, to understand the natural world. And that's what we use science for. That's what we use theories for. And theories are never really wrong or right. And this is why with the null is never really wrong or right. You just replace the null with a better understanding. So the whole thing with nulls and alternatives is science. We don't say we know general relativity is true. We're just doing what with general relativity? We are failing to reject it. We don't have a better model than general relativity. So at the present moment, we are failing to reject it. Einstein thought quantum mechanics is a mistake. Wow. See, Einstein, he was wrong about stuff. That is so crazy, man. Einstein is so crazy smart. Morgan, tell me if it's wrong. I don't know. I wonder if I can view the right answer. No theory is true. Yeah, no theory is true. He once claimed that the universe was static. Einstein did? Wow. No theory is true. A theory is merely our best understanding of an observed natural phenomenon, which is open to revision and better understandings. Because this is my last question before we do this problem. If you lived 1,000 years ago, which I think they would it be, would you be going with the best evidence if you thought the Earth was the center of the universe? An accepted theory would just be the predominant theory in the scientific community, or what we wouldn't say it's accepted, we would say it's the consensus among the scientific community. Maybe it's just me. Isaac might be saying it how people would say it. Being in the stats world, I would just say it's the scientific consensus, and it doesn't mean it's true. It just means it's kind of being in the stat world, I always hate the accept world. But would you be reasonable to believe the Earth was the center of the universe 1,000 years ago? And you probably understand where I'm going with this. It would be very, very reasonable to believe 1,000 years ago the Earth is the center of the universe. If you believed against that, you would actually be doing something you don't have good evidence for. Now, you would be right. You would be, I mean, at least as right as we think we are. I mean, we've got better theories now that explain that the sun is the center of the universe. And Copernicus, yep. And he's in chat. Hello, right there. You would be right. At least, I think we have you'd be right under our current model, I should say. So, yeah, it's just, is Brian saying the Earth is the sun is not the center of the universe? To the best of our understanding, according to the scientific models we have, the sun best explains the observed phenomenons we see within the universe, like the rotations. And a fact is something. The sun is not the center of the universe. Am I wrong on that? It's the center of our galaxy, right? Oh my gosh. Don't take what Brian says. It's the center of our galaxy. No, it's not the center of our galaxy. Solar. That makes sense. Can you tell statistics is my thing? Isaac, great job right there. Isaac, text on in chat. You're right. Isaac, please correct me. Sun is not the center of the universe. It's not the center of the Milky Way galaxy either. The center of our universe is the supermassive black hole in the middle. Oh my gosh, well that's fun. Hopefully it's not growing. So cool. Tell you how much Brian knows astronomy and stuff like that. So almost did astrology. Okay, you guys ready? I got another 30 minutes or so. Our galaxy is orbiting around another. Really? Galaxy's orbit? I should have probably known that. I should have probably known. Do we figure out what happens if you go through a black hole yet? I think time slows. There's like time dilation. Because it might have to do with general relativity, but I think spaghettification. Yeah, I've seen that, especially in sci-fi. I think it is theoretical. Like we have an idea, and it's based on our best knowledge, and obviously we don't know. And you see, then here's the difference between scientific theory and a fact. If someone went through a black hole, and let's say they survived it somehow, then it would be a fact of what happens to you when you go through a black hole. Like that would become a fact. Like you go through a black hole, and you time changes, and you slow down time for yourself. Who knows? But good luck with that. I agree. And then the why of how it occurs is the scientific theory. So when you observe gravity, when you see this phone drop right here, I didn't want to drop it on the keyboard, but when you see that phone drop, you are observing gravity. Now, why does the phone drop is the scientific theory. So it is a fact. 9.81 meters per second, which you observed right there, 9.81 meters per second is scientific fact. But why does the phone drop is explained by general relativity, which is Einstein's theory. I almost said the wrong person. But does that make sense right there? Scientific fact is the 9.81 meters per second. That's a fact. But then the observation of gravity via general relativity is scientific theory, which explains the observed natural phenomenon of 9.81 meters per second, which we label gravity. So little aside right there. Okay, let's do this question. We got a few more. We got time. I'm going to say at least one today. Exactly. Isaac knows what's going on right there. I love it. I love statistics. I love science. It's such a cool thing. Okay. So we've got right here, there's scores. We need to standardize these scores. Earlier, I asked a question that I got sidetracked for a little bit, had some fun, is that we see somebody's score is 7 higher on one thing, but the mean for math is 66, and the mean for economics is 75. They scored, if you look at their economics score, um, that could happen. Who knows? They scored a little less than 1 standard deviation above their economics average for the class. And the math score looks to be almost 2. It's almost 2. So since she scored, so how many was she above the mean for economics? It should be 0.8. How many? 2 decimals? Should be that because it's 5/6. So observation minus mean. I'm doing observation minus mean divided by, I typed it in wrong because that doesn't look accurate. Observation minus mean over standard deviation. That's 5/6 right there as a decimal. Great job, Gracie, in the chat right there. So we just did observation minus mean over standard deviation. Thank you for putting the things in the chat. You guys know what's going on. She's above the mean in economics. And then her, can I do the math one in my head? That's a trigger one. So that is 21. Can't do math today. 21, it's like 1.7 or something. It's going to be about 1.7. That's close. So observation minus the mean for mathematics. I said 1.7. It's 1.62. Close enough. If you can't tell, I like to solve problems in my head because if I make a guess, and that's also above the mean, she did better on the mathematics. Now, we should get it right. Please tell me we got it right. We got it right. Woo! And yeah, it's standard deviation, so it's not going to be z-scores. They just want above or below. Yeah, because if it was below, we would still be doing the standard deviations because it didn't say z-score. But the z-scores are still the same thing as the standard deviations here because they're both above the mean. So just more review that the z-scores are the same thing because they're both above the mean. There was another one. You're welcome, Gracie. Sorry that one took a while. Just had a little bit of fun between. Appreciate it. Thank you for staying the whole time right here. Which of the following statements did someone, was it Isaac? Did you have one? Isaac, can you repeat your problem? Because Eric has got one, and I think it'll be a quick one. Repeat your problem, Isaac. Which of the following statements about a z-score is true? A z-score tells us how many standard deviations a value is away from the mean. You got that. A z-score standardizes data. It does. A z-score is a measure of how extreme a value is. Yeah. If it's outside of like -3 or +3, it's an outlier. A z-score has a mean of 0 and a standard deviation 1. They are all true. Those are all facts we should know about z-scores. Those are all definitely true. Will you do a company manufacturer's rivets? You got it. That one was so quick. I was like, I can knock that out. Like that. We got it. A company manufacturer's rivets. Where are those rivets? Something rivet. I need to put an effect on this. I need to put a sound effect on that. I was so happy I figured out how to do like the alpha layers on those. You're welcome, Erica. No worries. No worries. I appreciate it. Double check your questions. Double check, ask. Never hurts. I'm here to help. And I appreciate you guys staying, doing all the work, doing the quizzes. That's what you guys get. If you stay, I start doing the problems you're doing so you can double check them. And it's easier to do when it's live because then you can like ask the questions. A company that manufactures rivets believes the shear strength in pounds is normally distributed with a model of 620. 600 means standard deviation 20. This means normally distributed. I don't know if 16% is low enough. I think that's not going to be so unusual. Yeah, because that's only one standard deviation below the mean. So if it's asking about if that's unusual. Now, Isaac, this is one people get wrong. If you're watching this problem right now, here's where people make a mistake. I want you to look at these graphics and tell me how many standard deviations are we looking at between these numbers. This is plus or minus how many standard deviations. This is a key, and this is where people make a mistake on this one. These numbers should be plus or minus 2 sigma. So people usually pick this one right here because it is going up and down by 20, but it's 2 sigma. So you have to understand that we're seeing here 2 standard deviations. With a standard deviation of 20, this would be 620 and this would be 640. How do I know it's 2 standard deviations? Because the middle 95 is within plus or minus 2. That's a trick to this question. Morgan, great job, Morgan. That one gets a lot of people. They're like, wait a minute. No, I'm like, oh no, don't worry. I'll get an email from someone saying, Brian, I did what you said and it was wrong. And I'll be like, no. I've taught this one a lot, if you can't tell. It is tricky. It is tricky. It's showing you that this is 2 standard deviations. Would it be safe to use these rivets at 580? That's 16. Well, the answer's got to be that. That's the only one. Yes, because nearly all rivets have a shear strength more than. This is a very, I know, right? Let's think about this. So the answer has to be this. They're trying to trick you with this one. Wait, yeah, because 580 is right here. Here's the thing. This is where we're dealing with how my Pearson wants to word it. And we'll know the answer in here in a second. So you will have the answer in the video. You will know the answer. I'll tell you why I like this answer. I think what they're trying to get at with this answer is they want you to know that 16% is below this. Like, this question could just be worded, what percent of rivets are below 580? The subjective part of this question, like, is it safe? Let's imagine this. We're only going to use one rivet now. And we're going to make a shelf to house bowling balls. And for some reason, it's only being held by one rivet. And so, what's the confidence interval? Good question. That'll come later. If we were going to make a shelf that's going to hold our bowling balls, and it's only going to be held by one rivet, and the rivet needs to hold at least 580, then 16% of the time the shelf is made, the rivet would not hold that amount of strength. Now, this is not... And I think I get it now. Okay, I get it. I know the answer, and I can explain it better. Let me do this. This is going to make it very clear. If having a rivet, once again, sounds like ribbit. If having a rivet below, here's your boss. Your boss comes to you and says, this is going to be a problem if any of our rivets can't hold 580. Like, of course, there's a bad rivet every once in a while. Like, yeah, okay, 1 in 1,000 rivets might have a problem. And this actually gets into Six Sigma, if Isaac has ever heard of that. But we're not going to talk about that right now. But if one of our rivets can't hold 580 pounds, then that's going to be a problem. And of course, there could be one random rivet that doesn't hold that. But what percent of the rivets are expected to not hold 580 pounds? What percent of the rivets are not expected to hold 580 pounds? 16%. That sounds like a problem to me, that there's a good portion. So would it be safe to use these? The answer is no. And what percent of the rivets would expect to be below 640? Well, 640 right here is 95 here, and 2.5 below here, that's 97.5. The other way to get that, I'll draw that answer, and I'm going to explain a bigger concept here. The other way to get that with your graphic, well, it's close to 1 out of 5, you're right. It's very close to 1 out of 6. Sorry, yeah, 6.666 is 1 out of 6. And so it's very, very close to 1 out of 6, and close to 1 out of 5 also. And that's how I was able to figure out 83.333 earlier. But, whoops, went to the wrong screen. My brain's jumping. I need food. The number right here, if we draw out our curve, we actually have this set up basically. Let's race it down a little bit. This is 600, this was 640, and this is 580. And so now the area above 640 is 2.5. So if the area above 640 is 2.5, the area below it, did it say a below or above? I hope it said below because I calculated below. So the area below it would be those areas right there, and the area above it would be this area right here. So you got a 100? Awesome. I got one more thing to tell you guys real quick. Make sure the area is below. That would be right. Did I get it all right? I got it right. One thing you kind of brought up right there, almost, and put the questions in the chat if you have them. I got time for a few more here because I'm going to go to Kingsport. Sorry, the video will be updated a good bit later. One thing you kind of brought up, Isaac, is a lot of times when we do process control stuff, you want to do something called Six Sigma. And that means that we meet our specs within 6 standard deviations. Because if you think about if you go outside of 6 standard deviations, it would basically be very, very few observations. Because what we're talking about here is, let's say we have a process where we make our rivets, and they say to us that the rivets can't be below 480. Well, that'd be really good for us because 480 with that previous model would be exactly 6 sigma below, 6 standard deviations below it. So we meet what is called a 6 sigma process right here, that we have at least 6 standard deviations, 6 sigma on it. And then when you look at it, there's really going to be like no rivets down here that would be, like this area right here is so very tiny. We can actually compute the amount of rivets that we would expect to have a strength below 480. We need to use things like R right here. So what we would do is we'd go to pnorm, and the amount of, so this should do the area, we'll do like negative, and no, we have to do it this way. I think this should give me 16%, right? Yep, cool. So that is computing correctly. And below 6 standard deviations would be that. Which when you think about this, out of how many rivets, like before we said with this, it'd be 1 in every 6 rivets. So basically 1 in every 6 or 1 in every 5 rivets. I think that's being calculated correctly right there. And then with this, it'd be 1 in every, holy majoli. So the amount of rivets we would expect to not meet specifications are 1 in every 101 million plus rivets. So if they said we really need to make sure that our rivets meet these specifications, we would make sure we have a 6 sigma process that and the way you can do this is you can lower your standard deviation. So you could decrease the standard deviation right here, but the amount of rivets we would expect now, if we need to meet 480 and our rivets have a strength of 600 with a variation of 20. Now this doesn't account for, we have to have a normally distributed process. We can't have a process that has like some sort of defect every once in a while, like in the material or things like that. But we might consistently test our rivets to make sure they're still normally distributed. And then we would expect 1 in every 101 million rivets to be outside the specifications. And I mean, that's about the best you can do. We can't promise because, I mean, we don't test every rivet because you probably have to destroy the rivet to see when it breaks. Like, when does this rivet, after, let's say the rivet needs to be tested for 1 year of pressure or something ridiculous. Could you help with one question? Yeah, Neil, let's do it. We got enough time for that. So I'll probably head off around 1 right here. I can copy and paste the question. Yeah, put the start of the question in the chat, and then I'll do it right here. Thank you, Neelan. Based on the normal model, describe the steer weights cut off for the heist. Yeah, oh, cool. So right here, we have a problem where you need the David M. Lane. So once you know how to do this, you're going to be like, no way, that's so easy. Like, I promise you. You ready? What do you think I'm going to put right here, Neelan? What will I put right there? What will I put right there? I'm going to have to do something else in a moment, but for now, I'm just going to use this one. So what do I have to put right here? You got it. And then I have to put 88 right here. Now, this is where people get stuck because they're like, wait a minute. Now what do I do? If you noticed, you have given me areas with the 10%, 20%, 40%, or you've given me values. Does 10%, yeah, no, that's awesome. This is where people get stuck on this one. Great question, Neelan. So this is where people get stuck on this one. Have you given me areas or values? Have you given me up above areas or values? Does 10% sound like an area, like a percentage on the curve, or a value, like a z-score? Does 10% sound like an area or a value? Don't worry if you get it wrong. Just want you thinking it over. You're ahead of the game right now if you get this done. Does 10%, it sounds like an area. It's an area. So we're going to go to value from an area. Now, we do have to rewrite these numbers again. It does change the curve. They don't sync between them. So you have to rewrite your values of 1159 and your value of a standard deviation of 88. Now we want the highest 10%. Now tell me left or right, where do you think the highest 10% would be? On the left side or the right side of the curve? The highest 10%. Could be down here. I don't know if that's high. The left side or the right side for the highest 10%. Where do you think the highest 10% would be? It'd be on the right side. Now what you could do is you could do that. This is how a test question could look. The highest 10% is the 90th percentile. Great job, Jack. Excellent work. I'll see you tomorrow. The highest 10% is the 90th percentile, but you could do it easier by doing the following and going to this. So 10% is above this point right here. That's what it's telling you, that this is 10% above this point. So the answer to your first question is this, however it rounds. Remember, you can pause the video here, check this out. We're basically doing your question right here because you worked ahead and I really appreciate that. What is the what is the lowest? So you could do the lowest 20% with the following. That's the lowest 20% because there's 20% here and 80% here. You could do weird stuff like this. Then this value is the middle 60. That goes starting here and here. So that's 20%, 20%, 60. But you could also do 20% and just do that. And that's the same value. Is this making a little bit more sense, Neelan, that I'm putting in the area I want to see on the curve? And then since I want the lowest 20%, I have to choose the below. And it's giving me below this point is the lowest 20%. That's how to read it. Below this point is the lowest 20% on the curve. Yes, that's what I like seeing, Neelan. Great job at looking at this. And then when you ask the question, you're like, okay, this is how it works. I'm getting it. I tell it the percent I want to see. Excellent job. And then the middle 40, you could probably guess it. I'm going to click between. I'm going to go 40 right here. Now, you could do this the long way. The long way of doing it would be to say this is 30, this is 30. You could do the outside. You can go right here. And now this is 30, 30, and that's the middle 40. So this answer you're seeing right here of this 1112 is the same answer You see right there. Because now I'm showing the middle 40, where here I show the outer 60. So that's the outer 60, which in the middle, the white area there is the middle 40. Which of the following statistics are changed by multiplying each data value by a constant? If you multiply by a constant, great question, Jose, right there. If you multiply by a constant, everything changes. Where's our everything change graphic? Here it is right here. You will see in the first set of values, we have 1, 2, 3, 4, and then we multiply them all by 10. So 10, 20, 30, 40. And we get right here that the mean and median would change. That's the center of the data. It was like 2.5, and now it's 25. The range changed. It was 1 to 4. That was 3, and now it's 10 to 40. That is 30. And then the IQR changed. It was 1.5 to 3.5, which is an IQR of 2. Now it's 15 to 35, which is an IQR of 20. So the IQR changed, the range of the middle 50%. So pretty much everything changed right there about the data when you multiplied it by a constant. Adding values to it, though, will not change the spread of the data. So if we were to take these values, 1, 2, 3, 4, and just add to them, now we see changes in a few things. We see changes in the red lines right here are changes. That's not a red line. Looks like I had the red selected, but I didn't. So that is the mean and the median changing. So the mean and median were 2 and 2.5. And then down below, the mean and median are 12.5. And also that changes the quantiles. The 25th quantile was 1.5. The 25th quantile down below is 11.5. And of course, the 75th quantile also changed. But the IQR does not change. The IQR is the range of the middle 50%. So the range on the top one is 2, 3.5 minus 1.5, IQR range. And the IQR for the bottom one is 11.5 to 13.5, which is a range of 2. Also, the range of the whole data set did not change here because it's 1 to 4, range of 3, 11 to 14, range of 3. So the things that changed here were the mean and the median, and the quantile 1, quantile 3 changed. And what did not change, the range, the standard deviation, and the IQR, because it didn't spread the data out more. It just kind of shifted the data over. Think about it, just took the data and went and shifted it over. I think it's got it. Another question. Who's got questions? We might head off here soon. I got to fix my Mega Mondays. Let's head back, see that Mega Monday screen again. So we can end class with some Mega Mondays. I think we've done it. We'll just say, hey, head out. This was a big class today. Do we have to? Yep. On days like this, when I give you EC, which we'll try to keep till Mondays and Fridays. I don't know. I don't know. You guys always can give me suggestions. Because like every day extra credit. Every day. Maybe I'll just do like 5 points on other days. But keep emailing me them. And if you don't see your points, if something weird happens with your points, please tell me. It's always good to check your points. If you don't think you got your points, just tell me. We're going to get a lot of people. But remember, you could be here getting tons of extra credit. Yep, email me. Make sure you use the right email tells all that fun stuff. You could be here getting tons of extra credit every day and still fail the class. How? You're not doing the quizzes. No. If you do the quizzes, I'm not saying... I will say this. If you get 100 on all the quizzes, we virtually found out it's impossible. I think you almost just make a B. If you get 100 on all the quizzes, get a 50. You wouldn't automatically have the B, but you would have to still do the projects and stuff like that. And the homework. If you do, like, you can fail the test and still do well in this class. Now, that's not my goal, but you need to make sure you're doing the quizzes. And probably the best way to do the quizzes is to come to class, learn the material, then stay a little bit after and do the quizzes and homeworks. I think that's, yeah. And if you do everything else, I think Morgan's right there. Nice job, Morgan. That's if you do everything. So you basically, we did that earlier. You basically, by doing all the work, can get a B in the class. If you do, this would have been done. Do all the work, make a B. And so, but still, I'm sure people want to make an A. But if you make a B by doing all the work, then making an A won't be so bad. And that's making like a 0 on the quiz, on the test. So you just got to do a bit better. Do better. Let's get some awesome grades here. The tests are not going to be easy. So keep doing the quizzes. That's my advice. I know the tests are going to be tricky. But with that in mind, don't be like, I'll just wait till, I know. I'm not saying I haven't waited till later at night to do quizzes and homeworks and stuff like that. I'm not saying I've had something due at midnight and I've been like, it's 11, let me start it. Of course I've done that. But this is Brian's advice. after class, hang around, do the quizzes. Great job today. Don't worry, some people have work, jobs, kids. I understand. Try to carve out as much time as you can to start early. And then today I'm going to be a little slower on emails because I am literally about to drive to Kingsport. Going to hop in the car, drive to Kingsport, and then I'll probably be back later tonight. So sorry, today will be a slower day on emails. So I'm probably gonna see an email at like 9 p.m. and being like, because I'll be going through emails when I get back and be like, Brian, where are you? I'm sorry. The percents on the canvas for grades don't match the syllabus. Oh, yeah, let me change that, William. William, please send me an email and say, Brian, change those. Sorry about that. I copied from previous semester. Good thing we're not that far in, so good thing it's not that confusing yet. Sorry about that. That's really appreciated, William. I did change it from mini term to be nicer for the structure I'm using, and then it was just one of those things I forgot to change. Definitely an error on my part. I think that's got it. I'm gonna go drink some coffee and have some yogurt. Any other last questions as we finish today on Mega Mondays? I love that little dude right there. He's so cool. Little Mega Man dude. Should just grab my other Mega Mans. Every Mega Monday, there'll be something new. I'll have a different Mega Man for Mega Man Mondays, because maybe I got a few of them. You're welcome, Morgan. You're welcome, Neelan. So great having you on here today. We're going to end with the Crash Bandicoot, because you know he's awesome. So I'll see everyone later. See you tomorrow. We got it.